to give a lecture on the topic Emerging Wireless Optical Technologies for IoT and 5G and 6G. Dr. Suman Kumar De received his BTech degree in Electronics and Communication Engineering from Jalpaiguri Government Engineering College, Jalpaiguri, in the year 2007, and he received his MTech degree in Electronics and Telecommunication Engineering from Bengal Engineering and Science University, Sipur, in the year 2010, and he received his PhD degree in Optical Communication and Networking from the Department of Electrical Engineering at IIT Patna in the year 2017. Currently, he is working as an assistant professor in the Department of Electrical Engineering in NIT Rourkela, Orissa. Prior to join NIT Rourkela, he also worked as an assistant professor in KITT University, Bhubaneswar, and NIT Jamshedpur. He is the author of several papers in journals and conferences of international repute. Dr. De's primary academic and research interests are in the field of optical communication and networks, wireless communication and network, and wireless sensor network. Over to you, sir.
Okay, very good morning, all of you. Thank you to Salam for giving a nice introduction of mine. So, myself is Dr. Suman Kumar, the assistant and assistant professor in the Department of Electrical Engineering, NIT Rourkela, and I am very much thankful to the organizer for giving me the opportunity to share my view on the emerging wireless optical technologies for IoT and 5G, 6G beyond with you. So let me share my presentation PPT. So is my PPT is visible to all of you?
Yes, sir. Yes, sir.
Okay. So basically, this is the outline of my today's talk. And first, I will give a brief introduction about the 5G, 6G, and IoT. After that, I will discuss about the key requirements of 5G, 6G, IoT, or the service offered by the 5G, 6G, and IoT. Thereafter, I will discuss about the different type of optical wireless communications technology and technologies and their advantage, limitations, and wide range of applications. So then I will discuss about the impact of the optical communications can provide the solution, how the optical wireless communication can provide solution for IoT and beyonds. And basically the beyonds in the sense I am telling about the 5G and 6G. After that I will discuss about the application of optical wireless communication platform which fulfill the service quality characteristics or fulfill the network and infrastructure characteristics. After that, I will discuss some open issue and future research direction in the wireless optical communications technologies, and followed by the conclusions. So, for the introduction, as we know, the new data rate, multimedia service, and application are evolving continually and exponentially increasing the demand for wireless capacities for 5G, 6G, and beyond. Thus, we can say the 5G and 6G communication is the next step in the mobile telecom communication standard. So, it will be offer new service with ultra high system capacity, massive device connectivity, ultra low latency, ultra high security, ultra low energy consumption, and extremely high quality of experience. So it is expected that the 5G communication will comprise ultra dense heterogeneous network for which mobile data volume per area will be 1,000 times and the number of connected wireless device will be 100 times higher compared to this existing wireless network. So therefore, upcoming the network must have the capability to support high user data rates and low power consumption and negligibly end-to-end delay. So end-to-end delay indicates over here the latency. So the high capacity vehicle connectivity is also essential for 5G and 6G or beyond communication in order to support hyper-dense, hyper-fast access network. So aside from these 5G and 6G and beyond, the Internet of Things IoT network is becoming increasingly important. A large number of end user device and sensor are connected to the IoT. Moreover, the internet will be the essential features of the future IoT, which will enable real-time communication system with range of society, industry, and business use cases. So the IoT based on the tactile internet will also be an essential part of 5G and 6G beyond communication system. So furthermore, with the development of the IoT concept, the rate of which the physical devices are connected to the internet is increasing exponentially. Therefore, the IoT generates a large volume of data. So currently, the radio frequency or RF is widely used across the various wireless applications. However, it's in relation to meet the growing demand of 5G wireless capacity and service of IoT paradigm, the current use of RF spectrum is insufficient. So the electromagnetic spectrum with the favorable communication property, which is below the 10 gigahertz, is widely used for by the existing wireless technologies and has almost been exhausted. Therefore, it is predicted that the massive connectivity demand of future mobile data traffic will be met by the existing wireless technology. Moreover, this band, which is below the 10 gigahertz, has limitation such as the small spectrum bandwidth, regulation related to the spectrum uses, and service interference among the nearby RF access point. So, at the World Radio Conference 2015, the International Telecommunication Union, the ITU, proposed 11 new candidate bands for international mobile telecommunications 2020, and that is 5G communication and beyond. So we know that the RF band normally lies between the 3 kilohertz to 300 gigahertz of the electromagnetic spectrum, which is strictly regulated by the local and international authorities. So in most cases, the RF subband are entirely licensed to certain operators like your cellular phone operators or television broadcasting or broadcaster and point to point microwave link. So thus the optical spectrum is considered as a promising technology for solution for the deployment of future high density and high capacity network. So basically the wireless connectivity based on the optical spectrum is termed as a optical wireless communication or OWC. Okay. So this is the figure the how the uh, evolution of the wireless technology. We can see that we started from 1980. The first G is came, then second G at 1990, then 3G is 2000 or 2K, then 4G 2010, and 5G is 2020. And we are also working, nowadays we are working on the 6G. So, and it is expected that the 6G will come in 2030, because if we look the history of the progress for the different generation of the telecommunication or mobile wireless evolution, so we can see that every 10 years there is a changes in the wireless communication. So definitely it is expected that it will change every 10 years. Okay. So now we'll see the what are the basic requirements of 5G, 6G and IoT one by one. So basically I will start with the requirements of 5G. So 5G will provide an order of magnitude improvement in some key characteristics compared to 4G to efficiently support the increasing heterogeneous multimedia applications with a diverse set of requirements. And the 5G system is expected to be fully deployed in 2020. And we have seen that in many countries already the 5G is deployed and they are providing service using the 5G. So the main key requirement for the 5G was the as follows. The first one is the massive connectivity. So basically it provides the massive connectivity 10 to 100 times more devices will be connected compared to 4G communication system. And high second is the high traffic volume. So basically the mobile data volume per area will be 1,000 times compared to that of the 4G wireless network, and the number of connected wireless device will be 100 times higher. So higher next is the high user data rate link. So basically the 5G network must have the capability to support a very high user data rate, and the user will be achieve up to the 10 Gbps data rate, which will be 10 to 100 times higher than or higher compared to the 4G. So next is the lower energy consumption. The lower energy consumption is a important requirement in the 5G communication system. It will reduce the energy consumption more than 90%, or we can say which is 10 times lower compared to your 4G. And it has a extremely low latency, and the end to end latency will within only the sub-millisecond levels of the in the millisecond. And there is a high security is there, so we know there is a high security is we can achieve using the 5G. Then high quality of experiences and support to integrate with the ultra dense heterogeneous network. So now we'll discuss about the some basic requirements about the 6G. So basically in the 6G, the key requirements for the 6G are similar to 5G. However, the in 6G it is folded by many times compared to 5G. So and 6G is expected to be the characterized by 1,000 times higher simultaneous wireless connectivity than the 5G. So whatever the connectivity, the number of users we can connect, or whatever the data rate we can use using the 5G, when we'll move to the 6G, that time the data rate and number of users accommodation will increase around 1,000 times, which is higher than the 5G. So it has the high or ultra high density network. Basically it provides the uniform quality of experience, the massive connectivity, then high capacity demand. 5G and beyond network deployment are expected to be much denser and comprise the ultra dense heterogeneous network compared to your 4G and 5G network. And in the 6G, the small size or small cells network is required. So the concept of high dense or small cells network has been pointed out as a core characteristics for the 5G and 6G or beyond communication system. So it has a higher spectrum efficiency. 6G and beyond system, or we can also say the 5G and beyond system, are also expected to guarantee an efficient use of the frequency spectrum by using the multi-input, multi-output, advanced coding and modulation scheme, and a few waveform design. The spectrum efficiency of 5G should be at least 3 times higher than that of 4G and 5G networks. So at the same time, it has the low cost of in the 6G. The 5G system basically, which is targeted to be or to be 100 times more efficient compared to the 4G by delivering the 100 times more data traffic using the same energy over the network. Similarly, when you talk about the 6G, that time the 6G will provide, or it is targeting the 100 times more efficient compared to the 5G system, which will definitely deliver the 100 times of more data traffic in compared to the 5G. So as a consequence, they will require low cost network equipment, lower deployment cost, and enhance the power saving functionalities on the network and user equipment side. And offloading of heavy traffic to the indoor. Basically, we can see that nearby 80% of the mobile traffic volume which is generated indoor, and uploading this volume of data to the indoor dense small cell are released expensive and valuable resources of microcell, because we are using the microcell, as I mentioned earlier, that we are using the very small cells, which is basically known as the microcells as well. So basically the resources of the microcell we need to consider. Hence that offloading of the data to the indoor small cell or microcell will be the another important characteristics for your 5G, 6G and beyond communication system. So in compared to earlier case, it has some complexity, or for connecting the massive network, the complexity will be more for the 6G. So now we'll discuss little bit about the or main requirements of the IoT. So the basically the IoT network also have the important characteristics, some key requirements of IoT system as shown over there. So these are the low device cost, then low deployment cost, higher energy efficiency, higher security and privacy, then support for massive number of devices. So basically we have seen when we discuss about the 5G and 6G, we already discussed about those points where the low cost devices, low means low deployment cost, those thing, energy efficiency. So these are there. So these are basically few requirements of the IoT. So now we'll discuss about the OWC technology. When we basically talk about the OWC technology, we can say that it is basically borrowed from the many trends such as 5G, then FSO, Carl Linders, and fiber, etc. Okay, so these are the borrowed from the OWC is borrowed from these four type of application or other trends. So basically, these four, what are the main OWC or optical wireless communication technology are there. So these are the four main OWC technologies exist over there in which the people are working. So the namely we can say the first one is the visual light communication or VLC. Second is the light fidelity or Li-Fi. Third one is the optical camera communication or OCC, and fourth one is the free space optics. So which are considered to be the promising technology to meet the demand of 5G, 6G or beyond network for their special features. So basically we can considering that it has the some promising features already is there, and the VLC that, or as I mentioned earlier, the VLC is the visual light communications which is used by the, we can see over there in this figure. So what are the medium, what are the transmitter and receiver using for the different type of communications, we'll see over there. So first the VLC which is used the light emitting diode and laser as a transmitter and photodetector as a receiver, and is it use the visible light as a communication channel or medium for the VLC type of communication. Then the Li-Fi, which is similar to your wireless fidelity or we can say the Wi-Fi technology, and in the Li-Fi it's provide the high speed wireless connectivity along with the users, and it use the LED or diffuse laser diode for transmitter or as a transmitter, and photodetector as a receiver. So it is used the visual light for the forward path. That means that we are using when we are transmitting the forward path for the communication, that is using the visual light. Or we can also similarly we can the forward path we can sometime mention as a downlink, and it is using the RF or infrared, VL or UV as a forward path for the uplink we are using as a communication medium for the return path. So in case of the OCC, which use the LED array or use a light as a transmitter and a camera or image sensor as a receiver. So the built-in complementary metal oxide semiconductor camera, which is facilitate the ability to capture the photo and video, and the camera can be either global shutter or rolling shutter type, and the OCC normally used for VL or basically visual light and infrared as a communication media. However, the ultraviolet spectrum can also be used for the communication medium. So the last one is the FSO or free space optics technology, which usually use the LED as a or the LD, the laser diode as a transmitter, and PD or photodetector as the receiver. So the heterodyne optical detection receiver is also used in FSO communication or free space optics communication. It is normally operated using the transmitter, the IR as well as the communication medium, but can also operate using the VL or visual light and UV, and all the terms that I used over here, the VL, UV, So it's already mentioned over there. Basically when we talk about the UV, that means it's ultraviolet light is using. So now there is some classification of OWC technology based on their transmission range. So basically the light allow the connectivity over the various range. So nanometer to greater than 10,000 kilometer of the communication. So based on this communication distance, the OWC system can also classify into 5 categories, which are namely the ultra short range, medium range, long range, and ultra long range. So basically in the ultra short range OWC, it is category of this OWC in millimeter or nanometer level communications are performed. For examples, we can consider the chip to chip communication. Second one is the short range OWC. So this is the wireless body area network or WBAN. So wireless personal area networks or WPAN and under the water communications are the few examples for using this short range of OWC. Then the medium range of OWC, this communication use comprising the VLC based WLAN and outdoor vehicle to other communication. So vehicle to other communication, sometime we mention as a V2X. So that means the communication will be held from the vehicle to other device. So next one is the long haul OWC. So this communication range provide the kilometer range of communication. For examples, inter-building connections. And the last one is the ultra long range. So this communication basically comprising the inter-satellite or satellite earth or earth satellite to airplane or airplane to satellite. So there are many examples is there. So basically these figures, bottom figure shows the classification of the OWC application based on the transmission range, and the OWC can be used for W band, B band, W band, and wireless metropolitan area network or WMAN, and wide area network or WAN, etc. So the application of the OWC system for the different range of communication, it show that the wide range of communication is possible over the OWC. So now the some examples is shown over there. So wireless communication is the optical spectrum is shown over there. So basically these are the electromagnetic spectrum that we use, and among this spectrum, which spectrum are used for the optical communication, and it is shown the visual lights over there. So the some important advantage of wireless communication is there, and when we are using the optical spectrum over the spectrum region, so what are the advantages we can get? So the advantages we can achieve from there, it has the huge unregulated bandwidth, then high level of security, because the light signal that we are using cannot the pass through the wall and can therefore be confined within a wall and define the coverage zone. Then the low power consumption is there. Whatever the power is consuming by these devices is very low, and for implementing those network, the requirement cost is very low, and the interferences of the electronics equipment or other communication network is almost negligible, and there is a possibility for achieve a higher SNR in this wireless optical communications using this optical spectrum. Then there are some obstacles, block transmission channel is there, and mostly we can, for when you talk about the wireless or optical wireless communications, so in that case mostly we use the line of sight of type of communication. So now there are many research also is going on for non line of sight communication, so it has some limitations. So what are those limitations? As that obstacle block transmission channels is there, and then sensitivity to sudden block a connections and limited transmitted power. So these are the some limitation. So these are the OWC technology which is using the IV, IR, VL and UV, and based on that different we have tabulated over there their applications or different characteristics for the IV, IR, VL and UV. So in the wavelength, we know what are the wavelength they are using over there. Then communication distance. So in the communication distance, different communication, or as I mentioned earlier, the what are the range for the communication. So based on that, the we can categorize for which type of communication distance, which type of spectrum we can use. Either we can use the IR or VL or UV. Then they have some advantages, and then there is some limitations and the communication technology we are using. So already I mentioned those things, and there is a basically we segregated there based on the different spectrum we are using for the communication in this, and we shown here as a tabulated form. Okay. So now this is the basic architecture of the different OWC technology. What is there in the block diagram? You can see this each optical technology has that unique characteristics or architecture and principle of operation. They have they may also differ in terms of the modulation techniques or transmitting system or receiving system, as well as the communication medium, but architecture almost the same. So basically in this figure show the basic architecture of this various OWC technology. And this some examples we are used there, architecture of the different OWC technology.
7 day is seeing, sir.
Okay, sir. Okay, so now we'll discuss about the some advantages and other phenomena for the different type of different or visible light communications, advantage, disadvantage or limitations. Those things we'll check, and where in which environment we can use, or either we can use for indoor outdoors. So we'll see one by one. So basically the VLC is a subset of OWC and has emerged as a promising technology in the past decades, and the VLC based on basically the LED and LD, and it can be promising solution for the forthcoming or upcoming high dense or high capacity 5G 6G wireless network. The IoT is become a increasingly important because it's allow a large number of devices to connect for sensing or monitoring or resource sharing. So for this kind of application, the VLC could play important roles at the end, and the VLC technology which offer 100 times more bandwidth compared to the RF based technology, and the VLC based on the VLCs or VL spectrum which provide the significant opportunity for application in home or office or car for aeroplane, train, and roadside. So in there are different applications is there. So and this not a harmful to the human. However, the technology suffer from a few limitation, and it is very effective for the outdoor applications, and it cannot perform long distance communications as we using the visual lights over there. So basically the LED can switch to different light intensive levels as a very fast rate, and which allow data to be modulated through the light emitting diode as a speed higher than the human eye which cannot detect it. Therefore, this energy efficient LED device can be used as a communication and localization or unique features nor which is not available the other device. So the potential of the VLC data rate is over 10 Gbps, which have already been demonstrated or by using the LED. So the data rate of 3 Gbps can be achieved using a single color LED, and the main disadvantage of this LED is the inherent trade-off between the bandwidth and optical efficiency. Therefore, the LED or laser diode LED can be considered as a promising alternative for the better utilization of the visual light spectrum for communication purpose. So when we are using the laser diode, a data rate of 100 Gbps can be achieved at standard indoor level or indoor application, and the VLC has many indoor outdoor applications like your smart lighting. So lighting used for VLC arrangement facilities, then communication and control simultaneously. Therefore, it can provide considerable savings in terms of the cost and energy consumption. Then wireless connectivity. We can create a high speed wireless connectivity with inherent security of the or by using this VLC. The LED based VLC can also use as to create the high speed local area network. Many car in our practical lab, many car already have LED lamp, and the traffic signal or traffic light and the street lamp or adopting this LED technology. This VLC create a great opportunity to create secure and high-speed data communication link for vehicle to vehicles or vehicle to infrastructure communication, or we can say the vehicles to other communication. So this RF-based communication which is not desirable at many part of the hospital, especially the MRI scanner and operating theater. So in the hospital, when we talk about the hospital, so in generally we avoid to use these RF based communications over there. So for such application, the VLC is a very good alternative to the RF based communications in hospital. So as we know, the RF is very much congested, and therefore the data can be overloaded or offloaded using the VLC, and the RF is desirable to for use by the passenger of aircraft. LED can also or alternatively used in aircraft for and can also be used instead of wire to providing the immediate service to the passengers that will reduce the cost of the aircraft construction and its weight. So now if we want to use the wire, so definitely in the aircraft, the weight of the aircraft will increase. So nowadays we are replacing the communications via this VLC. So in the underwater communication also, nowadays we are using this VLC which support the high speed data transfer in the underwater environment. Okay, these are the some basic structures is shown over there. How these sorry. Okay, so in these examples, different type of application where we can use is shown over there. Next is the light fidelity or Li-Fi. So basically, the Li-Fi can be classified as the nano or nano nm or nanomillimeter wave communications, and the main difference between the Li-Fi and VLC are the VLC basically use only the visual light portion of the light spectrum, whereas the Li-Fi can use the VL in the forward paths, and it is possible to use either IR or VL or UV in the return path. The VLC system can be either unidirectional or bidirectional, whereas the Li-Fi is a bidirectional communication system. So that means both direction of communication is possible using the Li-Fi. So Li-Fi provides the seamless user mobility, whereas the mobility support is not mandatory for the VLC. And the VLC or visual light communication system includes any of point to point or point to multi-point or multi-point to point communication, whereas the Li-Fi system must include the multi-user communication like point to multi-user or multi-user to point communication. So basically for using the Li-Fi, there is a no point to point communication is not normally happened, and hence the Li-Fi is complete wireless networking system and supports seamless user mobility. Therefore, in form of new small auto cell layer within the existing heterogeneous wireless network we can use, and the VLC system will treat as Li-Fi only if it has the Li-Fi features like the multi-user communication or point to multi-point or multi-point to point communication, then seamless user mobility. And on the other hand, the Li-Fi system can use or treat as a VLC only when the VL or visual light is used as a transmission medium. The term the Li-Fi, which is similar to your Wi-Fi, with the exception that optical spectrum used for the Li-Fi rather than the RF spectrum which is used for the Wi-Fi as a transmission medium. So the existence of the LED can use for the transmitter for in Li-Fi cellular deployment. So the along with this LED laser diode combination with the optical diffuser can also be used for the Li-Fi transmitter we have seen earlier, and we can achieve a 3 Gbps of data rate using the single micro LED, and which have already deployed in many applications, and there is a speed of 56 GBPS, which as if using the vertical cavity surface emitting laser, and the Li-Fi auto cell concept can reduce the cell size compared to your millimeter wave communication, and larger amount of data can be offloaded to the Li-Fi auto cell for congested RF based network. And the potential advantage of this Li-Fi over the Wi-Fi, which include the very fast data rate, low cost, and readily available spectrum capacity and better security. The security features of Li-Fi make it promising for offer the long distance communication. The few important difference between the Li-Fi and Wi-Fi is shown in this table. Basically, in based on that, transmission and reception medium, the maximum data rate, communication distance, interference level, transmission, then what IEEE standard used for these two, infrastructure cost, then modulation technique we used, then power consumption for communication purpose, and human toughness. Based on that, we are divided, or there is some difference between the Li-Fi and Wi-Fi. So some figure is shown over there how Li-Fi is used. So basically in the Li-Fi we are focusing for the indoor communication that I mentioned, and for the outdoor communication we rarely use because there is a huge noise effect will be there. So next one is the optical camera communication, OCC. So currently that we are highly habituated with the smart device in our daily life, and the majority of these devices are equipped with the front and rear camera with LED flash. These facilities of optical wireless communication implementation using the device that use a flash and camera as a receiver pair, and this implementation does not require any further hardware modifications. Therefore, there is a growing interest in the optical wireless communication implementation using the LED, a display, and other light source as the transmitter, and camera or image sensor as a receiver module. So although we are considering the research effort has been focused on the deployment of indoor VLC system, and there are remaining needs for research for the outdoor VLC system. So the challenges associated with the LED or photodiode based VLC and Li-Fi systems are some over here. The short distance communications, then drastic attenuation of received signal strength, then interference due to the artificial and natural light source, then noise due to the ambient light, radiations from the sun, skylight, or street light and other source of outdoor environment. The range or there is a large amount of noise from the background lights also is there, and the difficulties in detection of LED by the photodiode, especially under the direct sunlight. There is a huge difficulties is there. So furthermore, with increasing the transmission distance, small area photodiode is widely reduce the optical receiving power. Thus, there is a limiting of the transmission range, and this limitation can easily overcome using this camera or image sensor at the receiver. Okay. So left hand side of this figure we show the basic principles. Okay. So in the left hand side of this figure we show the basic principles of an OCC system. So the data is transmitting from two different LED transmitter, like your vehicle near the LED array and the traffic light. So that can be captured easily and distinguished simultaneously by using the image sensor and background noise source, light, sunlight or ambient light or digital signals over there can be discerned by separating the pixel associated with such noise sources. So easily from this figure you can see how the image sensor provide secure, interference-free, reliable communication for outdoor applications. And in the right hand side figures, we basically show few application scenario of OCC or optical camera communication system can use many indoor and outdoor applications, and the data monitors are wearable skin space can also be collected by using the camera. Then mobile user can share their data through the OCC technology. The OCC can also use to perform the motion detection and reconfigurations, and they can use to send the control signal by using the body motions, and OCC system can use to detect the such type of signals. So there are some advantages for the OCC. One is the non-interface communication. So when we talk about the image sensor, which is used as a receiver for the OCC, lights from the different sources are separated almost perfectly on a focal plane because there is a huge number of pixels in IS or image sensor, and the optical signals are output separately from the each pixels. So which avoid the signal from the becoming, or we can easily segregate those signals or mixtures, which is permitting communications even if the light signal and ambient light such as sunlight or street light are present over there. High SNR quality is present over there. The system or OCC system provide very high SNR levels, therefore requires no complex protocol for simultaneous communication among the multiple LEDs. The LEDs that are not required by receiver can be emitted entirely from image sensor because user can easily select communication partners from an image, and therefore there are no needs of complex signal processing to filter unnecessary information. The optical signal power received by the image sensor is stable against a changing communication distance. So if there is a changing in the communication distance, the received signal will be whatever the received power we are receiving by the image sensor, it will be fixed. So there are some limitation also is there in the OCC or optical camera communication. So in optical channel, as I mentioned earlier, which is basically we use the line of sight. Therefore, its communication links will be blocked by any objects that prevent light penetrations such as wall, building, or thick fog or thick gas. So there is a blocking of optical link is there. The OCC cannot support the high data rate communication owing to the low frame rates of conventional camera. The frame rates of commonly used for the image sensor is 30 pixel per frame or 30 frames per seconds, 30 fps, which is not adequate for achieving high data rate communication, and the data rate in terms of bps or pixel must be limited, and which is half of the frame rate, and it is less to signify the Nyquist frequency criteria. Therefore, for or to attain the higher data rates or high speed camera or newly developed image sensor should be used in the receiver signal. So the OCC has wide range of applications like the vehicle to other communications, then indoor positioning, then digital signage, which is basically the digital signage or display has become most popular medium among the business for broadcasting, advertising or messaging over the phone of customer. We are using the digital display. Then in the next generation, the world will be monitored using the drones. Therefore, the communication among drones is necessary to avoid drone to drone collisions, and the OCC can be future candidate for drone to drone communication. Virtual realizations of upcoming technology, the OCC can support this virtual reality service, and it provides the infotainment approach by the adapting certain machine learning approaches like artificial neural network or conventional neural network. Free space optics communications or FSO communications, which is one of the subset of your wireless optical communication, and it is normally operated using the NIR spectrum as a communication medium, and it can also operate using the VL and UV spectrum. However, when we using the IR, the attenuation level are lower, and there is a no illuminations is required for the FSO or free space optics. Free space optics often use the laser diode rather than the LED as a transmitter or for the transmission. There is a narrow beam of focused light from the LED transmitter or laser diode transmitter, which are used to establish high data rate communication link between the transmitter and receiver. The FSO system can use for high data rate communication between two fixed points over distance ranging from a nanometer to several thousand kilometers. So the FSO system uses the laser technology for signal transmissions, and in this figure show some basic block diagram of the FSO system. Because the optical beam forming long distance communication is possible for or using the FSO system or free space optic system. The source information data input is to be transmitted to a long distance. Initially, the source information is encoded, and optionally the channel coding can be used before the modulation. And the modulator platform normally use the on-off keying, phase modular, phase modulations, and OFDM modulation process. And the optical amplifier can also be used to increase the power intensity of the modulated laser beam. Then the light beam is collected and refocused by means of the beam forming optics before being transmitted, and typical optical source of FSO system is the laser diode. The optical source for free space optic system should deliver a comparatively high optical power over a wide temperature range, and the important features of the optical transmitter is FSO systems are size, power, beam quality, which determine the laser quality or laser intensity, intention, and medium divergence obtainable from the system. So the receiver front end comprising the optical filter with a lens to collect and focus the receiving beam into the or on the photodetector. The photodetector output current is the next convert to the voltage. There is a low pass filter is used to limit the thermal and background noise level. Finally, demodulator perform, which is necessary demodulation process to obtain the original sending data. So the frequency used for the free space optics communication, which is higher than the 3000 gigahertz, which is totally unregulated worldwide in comparison to the RF based communications or other communication. So the FSO or free space optics link have very high available bandwidth, which is providing or considerably higher data rates, and we can achieve the data rate up to 10 Gbps, which is having the already implemented for long distance communications. The 40 Gbps FSO link was also implemented in over a communication distance for 20 meter. A comparison between the FSO and microwave link, which is listed in this table, and there are various application scenario of FCs is shown in this figure. So now some comparison of the OWC technology is shown over here. So already we have seen that which type of applications or communication technology we are using, the communication distance, then mobility supports, environment effect, interface, data rate and security. So based on that, that is divided, or there is a comparison is shown in this figure. So the optical wireless communication technology for IoT and 5G beyond we can use, and the OWC support massive connectivity of IoT and high data rate 5G, 6G and beyond. So here we are using some small cells are using, then VLC or Li-Fi or OCC, which provide the ultra dense small cell hotspot service. FSO, Li-Fi and VLC can provide high capacity backhaul support for 5G, 6G and beyond communications, and it consumes very less amount of energy, and it provides the reliable connections, secure connectivity for indoor and outdoor communications, and the OWC offer extreme densifications and offloading to improve the spectral efficiency, as well as it is also support the IoT paradigm. So some applications of OWC platform. So basically so in this figure basically shows the some applications where we can use the OWC, and definitely when you talk about the OWC, that means 4 type of classification OWC we can use for the different type of applications over there. So now what is the fulfillment of the service quality characteristics is required. So first thing is the high volume of capacity. So it must higher bandwidth is essential to realize the 1000-fold capacity enhance in the 5G, 6G and beyond network. The radio frequency band, which consists of only up to 300 gigahertz of huge electromagnetic spectrum, where the optical band used from 300 gigahertz to 30 terahertz or more than, so basically it is 30 p hertz, which is considerably very high and available for wide applications or optical spectrum for the different OWC technology, and which is open for all because this is not regulated by the any authority local, either it is local or international. Ultra high user data rate we can achieve. The transmission rate of the 5G mobile communication or 6G system, which is expected to reach the 1 Gbps or 10 Gbps at the peak rate. So according to this, 6G will support 10 Gbps to Tbps bit rate per device. So the VLC and the Li-Fi technology have the capability to support very high data rate service at the user levels. Therefore, or moreover we can say the Li-Fi can support a complete network system. So like your point to multi-point or multi-point to point or bidirectional communications like our Wi-Fi at the data rate of your 100 Gbps, which is already confirmed using the VLC. It has the low latency, and the low latency is crucial for certain or key communication system or many of the key communication system, and is a more critical factor of your 5G and beyond communication system. The OWC or optical wireless communication system normally follow line of sight path. Hence the communication distance is minimum with no loss due to the obstruction. However, RF-based communications use both line of sight and non-line of sight paths. There is a significant loss due to the obstruction in non-line of sight path. Among the few important criteria, energy efficiency is one of the most important requirements for all 5G, 6G IoT system. Most OWC system infrastructure are based on the LED, and currently deploy the LED consume very small power, and there is a huge subsidy are already going around the world to reduce the power consumption by the LED. Reliable communication. So reliable communication is the important criteria for any kind of communication system, and the optical wireless communication system assure a very high level of SNR, especially for indoor users, even for the outdoor scenario. Then the OWC technology, which can also provide a secure communication as it is required for 5G, 6G and IoT network. So the fulfillment of the network and infrastructure characteristics, three primary means is there that can be used to add capacity to a network, densify the network, then making the spectrum more efficient and using more frequency spectrum. Network densification is defined as the adding of more cell site to increase the capacity. Then multi-tier architecture and convergence of heterogeneous network. So multi-tier architecture and convergence of heterogeneous network is basically to meet the demand of futures communications, and network will exploit a multi-tier architecture of large converged satellite or microcell network. Underlying small cell contain the RF small cell and optical, VLC, Li-Fi and OCC network. So each of the individual radio frequency and optical wireless communication has limitations and advantages, and the coexistence of heterogeneous network, that is your basically hybrid systems, consist of both RF and OWC technology, can effectively overcome the limitation. The presence of these two systems, that is RF and OWC, which provide the link reliable and providing a opportunity for load balancing. So massive connectivity is also crucial characteristics for the future communication system. The IoT in 5G is predicted to connect up to 50 billion heterogeneous devices, and these devices will be used in not only the mobile phone but also in other devices such as vehicles, household electronics, then medical equipments, and to basically to build a smart society. An effect of method An effective method of increasing the area spectrum efficiency is to string small cell size where a small number of users are served by a cell. To support the cellular connectivity and cope with the demand, the hybrid generation communication system consists only the microcellular network. The 4G system added small cell and microcell among with the microcell network, whereas the 5G system will contain ultra dense small cell among with the microcell network. Seamless movement of an essential criteria for considering any link of technology in the 5G and 6G beyond network, and the Li-Fi system offer complete mobility support to meet the demand of 5G and 6G communication. A backhaul is a network that connect with the access network to the core network, and current backhaul network mostly comprise dedicated fiber, copper or microwave, milliwave link, and occasionally satellite link. So backhaul connectivity using the satellite link depend on the availability of other options. High capacity of backhaul network is an essential part in the 5G, 6G and beyond system, and ability to exchange a large volume of data traffic between the access to the core network. The green communication can be achieved by several factors such as energy awareness in the network deployment, or choosing communication device, or design in the communication network protocol. Hence, the green aspect in the future 5G, 6G and IoT network required an energy efficient communication that can be effectively realized by increasing the use of the LED based OWC technology. Tactile network support, basically the International Telecommunication Union define the tactile internet as the future internet network that combine ultra low latency with extremely high availability, reliability, and security. Vehicular communication is an essential part of the modern era that promises to provide evacuations connectivity with the ultra reliable and low latency connectivity. So there are some open issue and future research direction in the OWC. The few important research issue and future direction are discuss over here. First one is the frequent handover. So future communication system will consist of heterogeneous small dense network that will create very frequent handover, and a handover will be between the optical network to the between optical or RF network. So as I told earlier that we are using very small cell, and the network we are using, they are supporting the different type of communication link. So that means when there is and it also support the mobility, so there is a huge probability for moving a device from one cell to another cell. So when we know for the cellular communication, when a cell is or a device is moving from one cell to another cell, there will be handover is required. So in 5G, 6G, there will be a possibility for frequent handover. So for that, there is a lot of research is going on how to handle those handover. And as well as I mentioned that we are using also the hybrid communication or network technology. So how to support that hybrid technology. Then the managing the intercell option optical interference, or the intercell optical interference is a serious issue in the deployment of optical VLC and Li-Fi network. The dense deployment of LED for the OWC technology may create high interference in the 5G and 6G and IoT networks. Therefore, the intercell optical interference is one of the challenging issue over there. Then the performance of the OWC technology is affected by the scattering, refractions, or air absorption, free space losses of the atmosphere. So in an outdoor environment, the fog, dust obstruct the optical signal from the transmitter to the receiver. The communication link quality in the free space optics is degraded because of atmospheric conditions. Hence, the atmospheric loss mitigation is a challenging with regard to reach the goal of our 5G, 6G beyond network, especially for outdoor conditions. Most of the users equipped with the design with low power LED to reduce the drainage of power. Because of the low power LED, the PLC and the Li-Fi cannot perform well in uplink communication. Moreover, more of the LED or light emitting diode of the user equipment produce diffuse light with low power that are easily affected by downlink high power light. Hence, limit of uplink communications. So in additions, a light deflections or movement of the receivers of a user equipment can easily hamper the uplink communication link. Hence, this is a important issue to be solved in future to efficiently support uplink communication using VLC or Li-Fi system. One of the most important drawback in the existing OCC or optical camera communication system is the low data rate. So it is a challenging to provide high data rate because the low frame rate camera we are using, and most recently achieving or we achieve the data rate in the OCC system is only 55 Mbps. This data rate should be increased to fulfill the demand of service in the 5G and 6G as well as the IoT network. So there is a huge research is going on to improving the data rate for specially OCC of type of communications. Flickering is defined as the fluctuation in the brightness of a light with, and that can be noticed by humans, and this is an important issue of the or in the OWC system or optical wireless communication system. Different modulation scheme on the OWC system may causes flickering that has a harmful effect on the human health, and the modulation of the LED should be done in such a manner that flickering is avoided, which is a challenging job also. The backhaul system in the 5G and 6G have to handle a enormously volume of data traffic to support high data rate service at the user level. Otherwise, a bottleneck problem will arise. Hence, the increasing of the FSO backhaul capacity considering the growth of traffic volume is a challenging task. So whatever the data rate is providing by the free space optics is not sufficient. So we need to improve that data rate in the FSO backhaul capacity. Then the learning based network system will be the key requirements in the future 6G communication network, and the ever increasing complex network structure and the requirements demand the artificial controlling and decision making in challenging environment. We can use the surprise or supervised learning for several OWC based applications such as smart healthcare, smart home lighting, and the OWC data mining. So in hybrid network architecture, which is a approach of integrates two or more different technology like OWC and RF, then free space optics, radio frequency, then Li-Fi, Wi-Fi, and so many. So in a hybrid network, and it capable to provide the advantage of both of the technologies, especially for optical wireless is a good candidate for sensitive application in which mitigating the interference with RF is a must, and hybrid network can play an important role for load balancing, link reliability improvement, then wireless connectivity in remote place, like your deep space or deep ocean or deep ground, and it's reduce the interference. Therefore, the issue is attracted by the researcher, and very important challenges of the hybrid system is to adaptability and smoothing switching from one communication system to the other communication system. So now extending the optical spectrum, the extending of the optical spectrum beyond the ultraviolet band can enjoy a lot of benefits from high power to the low cost sources, and this is a challenging issue for future wireless communication. In the recent year, underwater wireless optical communication attract mass attention as many applications are proposed for environmental monitoring, oil pipe investigation, offshore investigations, seamless mobility in OWC systems requires a requires to allow the user mobility. Currently, the only the Wi-Fi provide the seamless connectivity. Otherwise, or the researchers are basically working to support the horizontal handover of the OWC, for example, between the Wi-Fi networks as well as the vertical handover in hybrid network like Wi-Fi and Wi-Fi network. So it is very important to have handover mechanism to maintain seamless communication, and such a issue in the challenging and need to be properly studied. MIMO is already in well established technique in the RF based communication system. However, because of the properties of IM and DD channel, it is challenging to apply the MIMO in optical wireless communications. Currently, various RF-based technology are using in healthcare applications. The several medical devices are very sensitive to electromagnetic interference by the RF and can critically affect the performance of many medical devices. Moreover, the radio frequency radiation is not good for humans. So the LED based OWC can offer an excellent solution for the raised complication due to the huge of RF based wireless technology in healthcare and should be aimed to future research. Then the drone application. So basically drone is thinking as a next possible solution in transportation, and it is large scale deployment will raise several issues. For example, precise localizations, reliable communication among drones. The OWC can be a good complementary approach to solve this issue due to the limitation of RF based technology. A standard IEEE 802.11p, which is also known as the wireless access in vehicular environment, use the unlicensed RF band An OWC system or optical wireless communication system can also apply it for traffic management. Hence, the vehicular communication based on OWC technology can be a good research issue. So now these are the some conclusion we can make from our discussion, and more important and challenging issue for the IoT 5G and 6G are the provisioning the high capacity, massive connectivity, low latency, high security, low energy consumption, high quality of experience, and high reliable connectivity. Only the RF-based system are unable to meet this higher demand of the future 5G, 6G and beyond, as well as the IoT network. And the OWC technology are the best complementary solutions of the RF network. This study presents a detailed observation of how the OWC technology provide an effective solution for the useful deployment of future 5G, 6G and IoT network, and the application platform of each of the technology are different, as each of these technology has unique advantage and limitations. We have From this presentation, we have clearly differentiated between the basic principles, architecture, and application scenario, considering all of the mentioned OWC technology. So these are the some conclusions we can make from there. So, and these are the some references we used, and thank you. So if anyone have any question, they can ask.
Dear participants, if have you any query regarding this presentation, please ask, and also you can write your question on chat box.
Hello, sir.
Yes.
Sir, I want to ask that how OCC will be perform and operates in when there is a in rainy season. The rain will come between the object and that lens.
So, okay. So basically, this is the one of the limitation of the OCC system that we talk about. That when there is a interference is there, so some noises already might be is there, but we can differentiate those noises. But when we talk about the obstacles, because as I mentioned that for OCC communications, we require the line of sight of type of communications. So is there is any obstruction in between the source and that means transmitter and receiver, then definitely there will be a noise or the interference will be there. So definitely the examples you have told, which is obstructing the signal from receiving between the receiver and transmitter. So this is the one drawback of the OCC system. So we need to overcome those. If is there any technology we can develop? So whenever there is a rainfall, how to improve that OCC communications?
Yes, sir. Sir, in addition to that, how it operates in when the objects in motion in very high speed motion?
So basically, high speed motion means if you see that nowadays the camera is very sensitive enough that you can in the real life you can examples also when you are moving in like some high speed train or it might be you are moving in the flight, that time you also able to take some snap of different scenery. So basically that when you are moving, so when the lens is decided that we have to take the this is the source, so basically there is a alignment is there. So and there is a still there is a no obstacle between that. So the communication will established when you even though you are moving in the high speed. Definitely there is some limitation also is there that if you uh, move in a such place, there is a obstacle come in between the source and your receiver, that means transmitter and receiver, then you in this case it will not be able to detect that device or the objects. Okay. But if there is a no obstruction is there, then what we can easily get the signals from the transmitter, or there might be a possibility of communication between the OCC. And especially for this OCC, if you see that, okay, let me show you the so you see that even in this when we are moving in this your in which case we are using the OCC. So basically the we are using the means outdoor applications, and which is also associated with the many challenges is there, and especially that OCC we are using for the short communication distance. Okay.
Hello, sir.
Yes.
Sir, you were telling that sometimes in OCC it fails the Nyquist criteria.
Because okay, yes, I told that.
Sir, my question is, if it fails Nyquist criteria, then digital communication is not possible.
Yes, that.
Then only analog communication.
No, actually the thing is that Nyquist criteria is that whatever the for Nyquist criteria, what is the requirement? So what is the maximum frequency? And the Nyquist criteria is the 2 times of the maximum frequency of the signal. Okay, that is the minimum criteria. So we normally in practical scenario we sample the signal more than 2 times of the higher frequency of the signal. As we mentioned that how the if you just look at the operating principle of the camera, so in the camera there is a capability for capturing the frames. So when we are capturing the frames, that means frames per seconds, and normally the capacity is 30 frames as I mentioned. The 30 frames per seconds we can get. Okay. So now when there is a 30 frame per second is there, and in one frame how many bits we can transmit? So that is limited bits we can transmit. So we have seen that using the OCC we can achieve a very low communication speed, which is 56 Mbps. So now if we want to, that means when we talking about up to the 56 Mbps, that up to this it is satisfying the Nyquist criteria. And if we go beyond that, that means say if we talk about the 1 Gbps, so definitely that will not be, we cannot achieve that data rate using the OCC because it will not satisfy the Nyquist criteria. Okay, and whatever the communication techniques we are talking about for 5G, 6G and IoT, so most of the case we are using the digital modulation techniques we are using. Okay, so definitely you will see nowadays, you will see the most of the camera, the processor, digital image processing is they are using. So everything is the digital, in the digital form we are performing the operations. Okay, so the Nyquist criteria I mean, when I mention the Nyquist criteria, so that is basically the limiting the, for mentioning how it is limiting the data rate. Okay, because as we know that for successfully reconstruct a signal at the receivers, the digit or signal should be sampled at higher than the Nyquist criteria.
Yes, sir.
So to satisfy that, we have to stop in some portions or some frequency range.
Sir, that means below 53 Mbps, it will obey the Nyquist criteria. We can go for the telecommunications.
So yes, definitely.
Beyond that, there is a limitations.
A limitation is there, for that people are working how to improve those, because nowadays you may also see, if you have some observation on the camera technology, so people are working or they are trying to get a 60 frame per second type of shutter in the camera also. So people are working on that, how we can increase the frame per seconds in the camera. So as that number will increase, so definitely it will help.
Thank you, sir. Sir,
Yes.
system.
Your voice is not audible. Hello.
Sir, in conclusion, you have shown that backhaul system. What do you mean by backhaul system?
So basically the backend system, you see that when we talk about the backhaul system, that means there is a, in the network, so basically we use the two type of network is there. One is the code network and another is the access network. So basically when there is two network is there must be connectivity between these two, access network and code network. So basically the code network is connected with the access network through the backhaul communication link. So backhaul communication is provide the accessing between the two networks. One is the higher end, there is a core network is there. In the lower end, there is a access network is there. So suppose in the access network is providing service to the users, and the access network is connected to the core network through either a fiber link or free space optics or RF or satellite link. Many things is there. So basically the vehicle link, communication or link or system is the system which is basically connecting this two, or basically we can see it is a working as a interference between the interface between the access network and the code network.
Okay, sir. Thank you, sir. Sir, can you share the PPT so that we'll refer it?
Okay, then I will share to the Professor Kollan, and he will share to all of you. Okay.
Okay, thank you, sir.
Okay.
Any more questions?
Sir, I have a query.
Okay.
Good morning, sir.
Good morning.
Sir, in free space optical communication, we know that photodiodes are used as in receiver part. Okay,
Yes.
either we are using PIN photodiode or we are using APD photodiode normally.
Okay. So you
But nowadays, so
yes,
my
yes.
question is nowadays for free space optical for 5G backhaul communication. Now the solar cell receivers are used. Solar cell receiver. So
Solar cell as the
is
receiver.
there a solar cell as a receiver? So I just wanted to know is the solar cell receiver has any other advantage than normally PIN and APD photodiode, or for any other reason that receiver is used?
So basically, you see, depending on the applications we are using, suppose in some case, when suppose there is a when we are using the solar cell, basically in the solar cell you will see there are huge solar cells is there. Okay, so now if you just recall that sensitivity, when you talk about the sensitivity of a photo detector, so
Yes, sir.
photo detector is sensitivity is required, and if you see for the solar cell, so solar cell also a photo detector because it is detecting the sunlight photo from there and it is generating some current.
Correct.
Okay. So similarly, when we talk about the Avness APD or PIN photodiode, so their operation almost same, and depending on the application and technology, because as I mentioned that if we use some hybrid type of thing, like in this solar cell, if we use the solar cell, then what can be happened? The solar cell can be used when there is a light. Okay, light in the sense sunlight for generating the electricity, and sometime in the same time we may also use for the communications. So that means the solar cell is using for the hybrid type of communications or hybrid type of applications, you can say also. So like in a few years back there was a techniques, I think in some place also that technique is used, the how we can use the electric transmission line as a broadband line.
Yes, yes, sir.
So this thing is that people are trying to explore the different opportunities that we have, because if we compare the solar cell and the pin diode, both are photo detector, it is detecting the photo. Now how definitely there will be for if we use the solar cell as a photo detector for free space optics, definitely the signal processing over there will be little bit different. So people are working on that. So definitely till I hope that there is a no such practical applications, or they are trying to implement it in our practical life, because nowadays we are talking about the green communications. When you are green communication means if we use the solar, definitely there will be a green communications. So those things, due to that, there might be using. In, anyone have any more questions?
Okay, thank you, sir. I think there is no more questions there.
Okay, thank you.
So thank you, respected Dr. De, for giving us a wonderful session on emerging wireless optical technology for IoT and 5G and 6G. And also, Dr. De nicely present the future research direction of OWC and the optical camera communication also. So, from on behalf of our institute, that is NIT Manipur, I would like to thanks to Dr. De for giving us such type of presentation and on this topic on wireless or optical communication system. So thank you, sir.
Thank you.
Thank you very
Thank
much.
you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you all.
Okay, then I am leaving.
Okay, sir. Okay. Thank you,
Okay,
sir.
thank you. Thank you.
Now in this session, we will be having a lecture on the topic Plasmon assisted inline optical fiber sensor toward healthcare application. So for this session, Dr. Santosh Kumar is with us. Dr. Santosh Kumar received a PhD degree from IIT Dhanbad. He is currently working as an assistant professor with the School of Physics, Science and Information Technology, Liaocheng University, Liaocheng, China. He is also associated with the Department of EECE, DIT University, Dehradun. He has guided 7 MTech students at dissertation and 6 PhD candidates. He has published more than 160 research articles in national and international ACI journals and conferences. He has presented many articles at the conferences held in the Belgium and USA. He has published 2 books entitled Fiber Optics Communication, Optical Waveguides, Device and Application, and also another book entitled 2D Materials for Surface Plasmon Resonance-Based Sensors. He has reviewed more than 750 SCI journals of IEEE, Elsevier, Sprinzer, Optica, SPIE, and Nature. His current research interest includes optical fiber sensors, nanophotonics, waveguide, and interferometer. He is a life fellow member of Optical Society of India and a senior member of IEEE, Optica, and SPIE. He is also a traveling lecturer of Optica. He is also a chair of Optical Biosensor Technical Group. He has delivered many invited talks and served as a session chair of IEEE conferences. He is also an associate editor of IEEE Sensor Journal, IEEE SS, IEEE Transaction on Nanobioscience and Biomedical Optics Express. Over to you, sir.
Yes, thank you. Thank you very much for the nice introduction. And I hope I am audible.
Yes, sir. Yes, sir.
Yeah. So, good morning to all. And first of all, I would like to say thanks to invite me to Dr. Kalyan Mandal sir to invite me to give a talk in this FDP. And I would also like to thank to Honorable Director of NIT Manipur, and as well as one of my senior, Dr. Ashish Ranjan sir, to invite me to give a talk in this FDP. So in this talk in next 2 hours, and I think 1 hour 45 minutes, I will give a talk on the optical fiber biosensor and about its fabrication. And of course, that these sensors are mainly for the healthcare application. So nowadays, this is very important. The healthcare application is very important especially due to the COVID and the Omicron and the Delta variants. So I will also discuss about these things in this lecture. So before this, I would like to show a small video of our lab. So yeah. See? Yeah. So this is the introductory video of our lab.
山东省光通信科学与技术重点实验室，基于国家和山东省重大发展战略需求，立足于光通信与信息技术研究领域，坚持基础探索和工程技术相辅相成，光通信与光电子交叉融合的发展模式，先后建立了高速光传输、光通信技术等各类实验室20余个。 总面积为2360平方米，仪器设备总值达5000余万元。实验室现有教授19人，副教授25人，博士53人，形成了一支结构合理、创新能力强、中青年骨干发展潜力大的学术队伍。三头是库马博士，毕业于印度理工大学，2018年被聊城大学全职引进。 以三头身库马博士领衔的研究团队，主要从事基于干涉结构的生物传感器研发。此类传感器可在生物医学等领域准确地检测出蛋白质、葡萄糖等生物分子，利用金、银、纳米粒子等不同类型的纳米材料，可有效提高生物传感器的灵敏度，进而用特异性酶对传感器探针进行功能化，以提高传感器的选择性。2018年，团队获批山东省引进外国专家计划“一带一路”项目。三头身库马博士研究的光子开关器件及光纤生物传感器，迄今已在 Biomedical Optics Express、Optics and Laser Technology 等杂志发表高水平 SCI 论文100余篇，出版专著1部。此外，受邀担任 IEEE、Elsevier 等杂志社审稿人。SPIE 高级会员在国内外产生了较大影响。
We have a good research platform, a good research team, and a good research foundation. And we believe that with the support of this project, we can achieve good research result and promote the transformation of old and new driving force in the province.
该成果将进一步促进光纤生物传感器领域的成果转化，促进山东省经济社会的迅速发展，利用传感器探针低成本、可重复性的优点，实现快速、有效地检测出致褐氏菌，将有效控制我国第3大传染病细菌性痢疾的传播，在医学健康领域助力山东省新旧动能转换重大工程的实施。
So yes, thank you for listening this video. Then now I'm going to start my talk. So in this today I'm going to discuss about the Plasmon assisted inline optical fiber sensor towards a healthcare application. So yes, just I want to check, am I audible?
Yes, audible.
Okay, thank you.
Sir, if possible, your camera, can you open this? Actually, this video recording is.
Yes.
Is it possible or not, sir?
I think is it possible to share the screen and switch on the camera simultaneously? Because now it is okay?
Yes, yeah, okay, sir. Okay.
Okay. Thank you. Yes. So here I'm going to discuss about the Plasmon assisted inline optical fiber sensor that is for the healthcare application. So as I told, this is our university is established in a very beautiful city, that is the Owc city, and that is also called water city. And we have a very good experimental facility and for the fabrication, characterization, and the testing, and as well as for the clinical validation of the optical fiber biosensor. So yes. So here we can see. Yes. So till now our we have published 167 papers, and last year we have published around 40 high quality journals, and as per the Scopus we have I have reviewed around 750 research papers, and as editor handled the 175 papers, and so based on these credentials became SPI senior member in 2018 and IEEE senior member in 2019, and to Optica, that is the earlier, that is the OSA, so senior member in 2020, and as well as also became my associate editor of IEEE Sensor Journal in 2020, and in the last year became an associate editor of IEEE SAS Biomedical Optics Space and the senior editor of the IEEE Transitional Nanobiosensors. And from this year onward, on the chair position of the optical biosensor technical group. So in this we are going to organize the many optics related activities worldwide. So yes, in this today presentation, I will mainly cover the what about the optical fiber biosensor and what are those advantages and why, because earlier there are also so many sensors. So what are those limitations and what are the merit in our sensors? So I'll discuss about it and where this sensor can be useful SPR and LSPR phenomena. So nowadays these two phenomena is very popular to fabricate the high sensitive sensor. So I think in afternoon session also that will be given by the Professor Sanjeev Kumar Raghuvanshi sir, and that will be based on the LSPR. So SPR and my talk is mainly based on the LSPR phenomena. So these two talk will give the wide exposure of the fabrication of the sensor and facilities. So in this talk, I will mainly cover about the different type of the biomolecules detection. Biomolecules means those are found in the human body, like cholesterol, glucose, alanine, dopamine, uric acid, ascorbic acid, L-cysteine, collagen, picresol, and as well as I will also cover about the some of the bacteria detection, like Shigella bacteria that is responsible for the diarrhea, and as well as for the cancer cell detections. I will also discuss about these detections. So as we know, as per the WHO, I have just collected some of the data. So in as per WHO, 2.6 million deaths per year occur due to the change in the level of the cholesterol. Okay, due to the high level of the cholesterol or the low level of the cholesterol. So mainly the high level of the cholesterol, that is due to the bad cholesterol, because in cholesterol also there are two kinds of the cholesterol. So also in the liver, due to liver injury, around 2 million deaths occur per year. So and due to the cancer, around 10 million deaths in 2020 occurs. So and as well as diarrhea, around 0.6 million per year. Diarrhea mainly found in the developing country, and especially for the 0 to 5 years child, and this is very severe. And due to if there will be no proper treatment, so they may leads to death. So these are very critical things. So we need to detect these things, and the changes in these things means we need to diagnose this disease very early. And so for that we need to develop the portable, scalable and affordable and early diagnosis. And for this we need to develop the highly sensitive and selective sensor. So our goal is to the optical biosensor. Okay, so we will try to understand what is the healthcare, and for that, what are the optical biosensors. So here we can see in the block diagram, there are four kind of the things. So first is sample. Okay, so sample, let us assume that sample may be the glucose, cholesterol. Okay, and so for those particular samples, we need some specific biorecognition element like enzyme, antibody, protein, nucleic acid, etc. So that particular biorecognition element will combine with those particular things, and there will be some variation will occur at the surrounding of the sensor surface, and that variation will be recognized by some of the optical transducer. Okay, so there are so many optical transducer like SPR, LSPR, interferometers, resonators, gratings, refractometer. Okay, so nowadays, as I told, that SPR and LSPR is quite popular, and it is highly sensitive, and it also requires very less volume for the detection. So sorry. Yeah, so this will detect and we can get the output in the computer. Okay, so here we can say that biosensor detects a chemical or biochemical substance by transducing a biological interaction into the electronic or optical signals. Okay, so here we can do the sensitive and selective detection of a wide range of analytes like biomolecules. I told biomolecules means any kind of the biomolecules that found in the human serum or blood, and bacteria, virus, and toxin, drug, antibodies, tumor cells. Even virus, coronavirus can also detect through this kind of the optical biosensors. Okay, so what are the advantages of optical fiber biosensor? So first advantage is that it is biocompatible. Okay, so even we know that optical fiber is made of the silica, so we can insert inside the human body, or we can use it in the serum or some biological fluid, and there will be no any side effect. So that we can say that this is the biocompatible, and reduced size, flexibility, and low weight. So due to the flexibility in nature and so small size in nature, even we can insert inside the human body, and we can diagnose some things without any surgery. So this is the great advantage of this kind of the technology. And third is low cost. Everyone know that of course initial cost will the instrumentation will be high, but overall detection of the development of sensor and sensor per unit will be a low. Okay, so capability to work in hazardous media. So optical fiber sensor we can use it in nuclear environment, undersea, and we can use it any places, and so this is a great advantage of this kind of the sensor. Electromagnetic interference immunity. We will try to understand this one in this property. So in microwave, that wavelength is in the range of centimeter. Okay, so if the distance between the two wire will be in the range of the centimeter, it will be in the range of the wavelength comparable to wavelength, then there will be chances of electromagnetic interference. Okay, but in the optical fiber communication, due to the high frequency, the wavelength is in the range of micrometer. Okay, so it is very difficult to that there will be a distance of two optical fiber will be in the micrometer range. Okay, because there is a core cladding and then jacket, so there is very difficult that the distance between the two will be a micrometer range. So there are less chances and there will be no electromagnetic interference immunity occurring in the optical fiber communication or optical fiber sensor. Okay. So this is a great advantage. Multi-parameter sensing. Yes, nowadays people are developing multi-parameter or some kind of, say, we can cascaded sensor. So instead of the single kind of the detection, people are developing three sensor in a single chip. Okay, so that they can simultaneously detect the three parameter like humidity, temperature, and strain. Okay, like similarly in glucose, cholesterol, uric acid, simultaneously three kind of the things can be detected using the one sensor. So we can do the multi-parameter sensing. We can do the optical fiber communication. Okay, diversity of light propagation configuration. So we can mold the light flux in any configuration, in any desired configuration, and we can do the sensing. Okay, so this is the great advantage, and we can develop the sensor as per our need. Okay. So what are the application of the optical fiber biosensor? So there are two kind of the applications, one in the chemical sensing and another in the biosensing. So here in this talk, I will discuss mainly about the biosensing. in the second half of the talk, Professor Raghuvanshi sir will discuss about the chemical sensing, like the gas sensing and some other type of the chemical sensing. Okay, so here we can see the water quality we can see in the left side water quality pH sensor. In the right side, water quality pH sensor, CO2 sensor, volcanic sensor. So these are the kind of chemical sensing. Okay, so and in the left side, we can see the glucose sensing, nucleic acid sensing, bioanalysis, cell detections. These are the kind of the biosensing applications. So for these things, people are using the different kind of the optical fiber structure, like different kind of the interferometric structure, Michelson interferometer structure, magenta interferometer based structure, fabric based structures. Okay, so and also the different kind of the fiber bracketing, like east fiber bracketing, tilted fiber bracketing, and tapered fiber, SPR, evanescent wave based sensor, and long period grating based sensor. So these are the different kind of the optical fiber structure used for the development of the sensor. But these structures alone are not very sensitive. So to further enhance the sensitivity of these kind of the sensor, people are using the different kind of the nanomaterials, like the polymer, carbon nanotube, graphene oxide, nanoparticles like silver nanoparticles, gold nanoparticles, okay, and nanowires. Sorry, DNA. So these things are further enhancing the sensitivity of the sensor probe. Okay, so we can see nowadays 2D materials, two-dimensional materials like graphene oxide, MOS2, MOSE2. These are also very popular to increase the sensitivity further. Okay, so here we can see there are wide application of optical fiber biosensor even in day-to-day applications, like for the explosive gas detections, water quality, indoor air quality, humidity. So these are like a kind of the chemical sensing, and some biosensor, air quality, bacteria and virus. These are the biosensing type. So even we need to use the this kind of the sensor in the future in the day-to-day applications to keep our family happy. And so overall we can say that there are wide application of fiber optic plasmonic sensor, like in the chemical sensing, temperature sensing, environmental monitoring, pressure sensing, biomolecule sensing, force sensing, food safety, lab on chip, lab on fiber, medical diagnostic. So these are the biological applications of sensor. Okay. So now we will try to understand the phenomena, which phenomena is mainly working for this kind of the sensing. Sensing. So here the plasmonics. This is we can try to understand this term. This is a kind of the coherent oscillation of electron at metal dielectric interface. Okay. So when there will be a metal dielectric interface and we launch the light, then at the interface there's there will be oscillation of the electrons will occur, and that is the kind of the plasma and or plasmonics. Okay, so there are two kind of the this phenomena can occur. One is due to the thin film based, and another is based on the nanoparticle. Okay, so thin film based is called also called as propagating surface plasmon. Okay, and in that thing, the collective oscillation of conduction electron at metal dielectric interface under the influence of incident electromagnetic radiation will occur, and we can see that this kind of the electric field intensity will arises. But in the case of the nanoparticles means the size of the particle will be less than 100 nanometer. Okay, so in that case, the density oscillation of conduction electron inside metallic nanoparticle under the influence of incident electromagnetic radiation. So, sorry. Here, here we can see in the case of the thin film that surface plasmon resonance occur at the surface of the both metal and dielectric. But in the case of the nanoparticles that occur at the surrounding of the metallic nanoparticles, you can see this is this electric field intensity that arises at the surrounding of the metal nanoparticles. So in this case, this surrounding is very sensitive to the any external changes. Okay, so if there will be any change in the external surface, that will be recognized. And okay, so here we can see, we can also try to understand in the case of the optical fiber communication. So on optical fiber sensor, so here this is the first one is the SPR and second one is the LSPR. So in the SPR, this is the optical fiber structure. So in optical fiber structure, to fabricate the sensor, people are removing the cladding from the surface. So why they are removing the cladding? They are removing the cladding to get more and more evanescent wave outside the surface. Okay, so there are core and cladding. So we are launching the light at the core, and here we can see here the cladding is completely removed. Sometimes people are using the hydrofluoric acid, HF acid, to remove this kind of the cladding. Okay. So in there is a coating of the thin film around 40 nanometer and 60 nanometer kind of the coating of the like a gold or silver thin film, and above that this surface is working as a sensor. Okay, so here we can see when we are launching the light, so there is a one evanescent wave. Okay, and another kind of the wave is generated that is called as a surface plasmon wave. So this phenomena occur only due to the polarized light. Okay, so when the propagation constant of the evanescent wave and the surface plasmon wave will match, then this resonance will occur. SPR, surface plasmon resonance, will occur. Okay, but in the case of the LSPR, in this figure, second figure, we can see uh, when we launch the light, then that SPR will occur at the surrounding of the nanoparticles. Okay, and the advantage is that in this case there are no need of the polarized light. Any kind of the frequency can generate and can excite or the localized surface plasmon resonance. Okay, so this is the one of the kind of the advantage. So you can you can see in both the figure. In the first figure, there is a coating of the thin film of the nano material, and in the another figure, there is a coating of the nanoparticles. So okay, so here we can see how it is helping in the detection. So like this is the one kind of the nano material. So I told that for the specific recognition, we need to put some biorecognition element. Okay, so here we just like there is a biorecognition element like a glucose oxidase is coated over the metal film. So when we'll keep the put the our sensor in the glucose solution, then it will react, the glucose oxidase will react with the glucose, and it will produce the gluconic acid and H2O2, hydrogen peroxide. So change in the concentration of the hydrogen peroxide changes the refractive index of the surrounding of these gold nanoparticles, and due to this change in the surrounding refractive index or change in the surrounding medium, there will be a shift in the peak resonance wavelength shift in the peak resonance wavelength. And based on the shift wavelength, based on the shift resonance wavelength, we can determine the concentration of the analyte. Okay. So this is the simple funda of this kind of the optical fiber sensor. So our research group has developed the several type of the prototype of the sensor based on the different kind of the optical fiber structure, like the gender interferometer based structure, we with the combination of the different kind of the fiber, like single mode fiber, multi-mode fiber, single mode fiber, like this. And as well as our group has also developed the tapered fiber and multi-tapered fiber, and fiber ball, and we have also used the 7-core fiber, and we have eased and expanded the core, and we have also used the eased expanded fiber. And here we can see we have also done the detection from the serum of the human blood. So, and we have compared the sensing performance of our proposed sensor, developed sensor, using 10 instrument available in the clinics, and found it in the comparable similar. So we can say that sensor is also useful for the clinical applications. So here we can see yeah. Here, I'm going to say this is recently published in the last month, and this one is a very good structure, and that is the taper fiber structure, and this is very noble structure, and first time our group has developed this kind of the optical fiber structure, sensor structure, and shown the biological detection. So this is the taper fiber structure, and that is developed the LSPR sensor for alanine aminotransferase detection. So this is the another kind of the biomolecules, and that mainly produces during the liver injury. Okay, so when there will be one critical condition of the liver, or there will be some liver injury condition, so in that time the amount of this kind of the biomolecules are increases in the blood. Okay, so we can even detect and we can recognize this kind of the disease, or we can confirm that there is some injury, there is some liver injury, and we can do the treatment accordingly. So this work we can see. So this one is recently done by the collaboration of IIT Bhubaneswar and in our lab, as our lab. So here we can try to understand how we have fabricated and what is taper structure. So normally in taper structure, there is one tapered, like here we can see this is the 80 micrometer taper structure. We have used the 125 micrometer of the optical fiber structure, and after that we have tapered, and we have found the 80 micrometer taper structure. We have fabricated the 3 structure to show the repeatability, and found that the all structures diameter is approximately same. Okay. So what happened after fabricating the 80 micrometer, we have chosen the center part of the fiber, and we have tapered the same fiber again for the 40 micrometer. You can see in this figure. So that's why this is the tapered structure. So here we can see we have used the very machine that is combining manufacturing system in that there is a 3 electrode, and these 3 electrode and heated the complete 360 degree of the optical fiber structure, and there is a two clamp, that left clamp and right clamp, and these clamps stretching the fiber structure, and due to that there is some tapering phenomena occur, and of course these phenomena occur in the partial vacuum. So initially created the vacuum inside the CMS machine, and after that this phenomena occurs. So, and after that accurately locate the secondary discharge area and taper that fiber again. So here we can see initially the cladding diameter was 125 and the core diameter was 9 micrometer. So tapered, and after tapering it became 80 micrometer, and again it tapered and it became 40 micrometer. So here we can see in the tapering area the some part of is 80 micrometer and the center part is 40 micrometer. So due to that when we launch the light, you can see in this figure, when we launch the light, the some due to the tapering, more and more evanescent waves are coming outside at the sensing surface, and that evanescent wave is interacting with the metal coating. I mean, here we have used the gold nanoparticles, so that is interacting with the metal coating, and that is helping in the sensing. Okay, so here you can see in this case with the three different kind of the nano materials. So here we can see, and this is the tapered structure. Actually there is a limitation of the instrument SCM also, that we cannot see the complete structure simultaneously even at the lower magnification. This is the minimum magnification, that is the 29x. Still we can see the half part of the fiber, that is you can see the tapering occurs at this surface. So at the higher magnification, we have analyzed the three different kind of the sensor probe. First, after the coating of gold nanoparticle. So here you can see the gold nanoparticles are properly attached over the sensing surface. So here gold nanoparticles we have synthesized in our lab. So how we have synthesized? We have used the very popular turquoise method. So that is developed in 1951 or 52, and in this protocol we need to use the chloroauric acid and sodium citrate, trisodium citrate. So based on the concentration and volume of the chloroauric acid and trisodium citrate, we can vary the diameter of the gold nanoparticles. Okay, so here we can see the gold nanoparticles are evenly distributed after the coating process. So I will also again discuss the complete the synthesis process, characterization process, and immobilization process in detail. So here we can see in the second structure there is a coating of gold nanoparticle and molybdenum disulfide nanoparticles. Okay, so in the molybdenum disulfide nanoparticles are just looking at the top of the gold nanoparticle, and in the third figure, we after the coating of MOS2, we have also coated the cerium oxide nanoparticles. This is the unique kind of the nanoparticles and mainly used for the biological applications. So in this sensor structure, we have used the three kind of the nanomaterials. So in that, gold nanoparticles are helping in the LSPR phenomena. Okay, and the MOS2 and cerium oxide nanoparticles are increases the biocompatibility or the biological property of the sensor probe, and to increase the selectivity and increase the strengthen the sensor probe. So here we can see this is very special kind of the sensor in that we are not directly determining the concentration of biomolecules. We are determining the concentration of the enzyme. So here, in prior to detection, we are doing the some reaction of the enzyme, that is the ALT enzyme, alanine aminotransferase enzyme, and after the reaction, the byproduct we are detecting through the optical fiber sensor. And here we can see this is the complete setup structure, and for the detection of this kind of the byproduct L-glutamate, and based on that we are determining the ALT concentration. So here we have taken this kind of the ALT concentration and detected through our proposed sensor, and this sorry. So here we can see the linearity of our sensor probe is around 110 unit per liter to 1000 unit per liter. Okay, so and it is very selective, and very selectivity is high for the ALT enzyme and not for the other kind of the biomolecules. So this is the great advantage of this kind of the sensor probe. So here in the second case, I will explain the complete fabrication process in this work. Second work is ultra sensitive cholesterol sensor using gold and zinc oxide nanoparticles, immobilized core mismatch, MPM and SPS probe. So this work is very good work, and it is published in the IEEE Journal of Owc Technology. So here we can see, everyone know that cholesterol is produced by the liver, and it is also a part of the healthy diet because it is a precursor of a very essential biological materials such as bile acid, steroid, vitamin D of the human body. So, high level of the cholesterol in blood may cause several common disease such as hypertension, heart disease, coronary artery disease, cerebral thrombosis, arteriosclerosis, and low level of the cholesterol also causes the various diseases such as anemia, hyperthyroidism, malabsorption. So we need to develop sensor so that our sensor can detect the low as well as high both concentration of the cholesterol. So here we can see our group has developed the two different kind of the sensor structure. One is a combination of the multi-mode fiber, photosensitive fiber, and multi-mode fiber, that is the MPM sensor probe, and another is single mode photosensitive and single mode sensor probe structure. So here we can see, and we have also synthesized the two different kind of the gold nanoparticle, and also used the zinc oxide nanoparticles to further enhance the performance of the sensor. So we found that the normal concentration, cholesterol concentration in our human body is around 5.17 millimolar. So that we have developed a sensor which linear range is 0.1 to 10 millimolar, means that covers the complete detection range of our low and high concentration of our human cholesterol found in the human serum, and its limit of detection is also quite low. That is the good that the smaller amount of the cholesterol can also determine through our this developed sensor. So here you can see there are two kind of the optical fiber structure, that is the multi-mode photosensitive multi-mode. So it's the core diameter of multi-mode fiber is 125, and cladding diameter is core diameter is 62.5 and cladding diameter is 125 micrometer. And similarly for the photosensitive fiber, the core diameter is 4.2 micrometer and cladding diameter is 125 micrometer. So here we can see there is a difference in the core mismatch, because the core of the one fiber is 4.2 micrometer and another is 62.5 micrometer. So when we will launch the light, then some part of the light will go to the core of the fiber, but most of the core mode will go into the cladding of the photosensitive fiber. So that cladding mode will try to come outside the surrounding, and that will be helpful in the sensing purpose. Okay. So in another structure, we have used the single mode fiber, and instead of the multi-mode fiber. So here I told that we have also developed two different kind of the gold nanoparticle to know the which kind of the gold nanoparticle is better for the sensing. So here, as I discussed, using the variation of trisodium citrate volume and concentration, we can synthesize the different kind of the gold nanoparticles. So here the 10 nanometer and 30 nanometer, which primary observation we can do using the UV visual spectrophotometer. Okay, in that we can see if the peak resonance wavelength will be 519, so that will be a 10 nanometer of the nanometer, and if the peak wavelength will be 527 nanometer, then its diameter will be 30 nanometer. Okay, so similarly we have measured the Jorgensen spectrum of zinc oxide, that is around 370. So here we have purchased the zinc oxide nanoparticle directly from the Sigma company, and here we can see these are the TM image of the gold nanoparticles. So the first one is 10 nanometer and second one is 29 nanometer. The scaling diameter is different, that's why the look is it seems look is looking different size, but the second one is the smaller one. Okay, so we can also measure the diameter through the image software, and we can plot the histogram of the nanoparticles. Okay, so yeah, this is very important. After synthesis of the nanoparticles and fabrication of the fiber structure, how we can do the coating of the nanoparticle on the optical fiber structure. So for that, firstly we need to follow the cleaning process. So we need to follow the 3-step cleaning process. In the first step, we need to put it in the acetone for the 20 minutes. Then we need to put it in the piranha solution for the 30 minutes, and we need to wash with the water, and we need to dry in the oven. So this process produces the OH group over the optical fiber structure, and then we need to put it in the MPTMS for 12 hours, and that is the ethanolic MPTMS. So that process produces the SH group over the optical fiber structure. Okay, and after that, and we need to put it in the gold nanoparticle for 48 hours. So we have used the deep coating method to coating of the nanoparticles, and after 48 hours we need to rinse with the ethanol and dry with the nitrogen gas, so that it can remove the unbounded nanoparticles. Okay, so after that we have followed the annealing method to coating of the zinc oxide nanoparticles. So we have dipped in the some concentration, and after that we have heated, and finally we have developed the sensor probe. So in this process we have these are the kind of the immobilization process of nanomaterials or nanoparticles on the optical fiber structure. After the coating of the nanoparticles, again we need to follow some of the chemical process to do the coating of enzyme over the sensor structure. So for that we need to do the coating of MOA, and that produces the carboxylic group, and after that put it in the EDC NHS for around 30 minutes. That activates the carboxylic group, and we need to put it in the cholesterol oxidase for the 12 hours, and that helps to add the enzyme on the sensor structure, and later on that is helpful in the sensing process. Okay, so this is the complete nanoparticles and enzyme functionalization process. So after coating, how we can verify that our nanomaterials are properly attached or not? So for that we need to do the Acm analysis. In Acm, scanning electron microscope, we can see the nanoparticles over the sensor structure. Okay, so here we can see we are able to see the gold nanoparticle and zinc oxide nanoparticles. But how we can say that this is the zinc and this is the gold nanoparticles? So for that, there is one more Acm EDX. So we can do the Acm EDX or EDS, and we can determine the material composition of the sensor structure. Okay, so here we can see the Zn is due to the zinc oxide, and Au is due to the gold nanoparticle, so are available on the sensor structure. So after that, we have also done some of the structural optimization process to know the center wavelength, the length of the center fiber, and etching time. So for the etching time, the 20-minute etching time is good. For in that we are getting the highest evanescent wave, maximum evanescent wave at the surrounding surface, and at that time the diameter is around 70 micrometer. Okay, so after fabrication of the sensor structure, we have prepared some concentration of cholesterol using the buffer tritone 5% buffer solution, and we have detected through our developed sensor structure, and we found that there is some linear variation. Okay, so in that we found that the 10 nanometer gold nanoparticle based sensor structure is better than 30 nanometer of gold nanoparticle structure, and we have also verified that the more core mismatch are good for the sensing purpose, so that MPM sensor probe is better than the SPS sensor probe. So we have also verified the selectivity test and found that it is selective for the cholesterol, because we have used the cholesterol oxidase that reacts with the cholesterol, that not reacts with the other biomolecules. Okay, so we have also done some of the other performance analysis like reusability, reproducibility, and found that our sensor is the highly reusable and reproducible. So overall in this sensor we can say that the smaller diameter is more sensitive, and the more core mismatch creates the more sensitive sensor. So here Dr. Mandal, sir, I would like to take a break of 5 minutes. So can I take a break of 5 minutes? Hello, sir. Are you?
Yes, sir. You can take.
Okay, so I will start at after 5 minutes.
Okay, sir. Okay, sir. No issue, sir.
Okay. Yes, sorry for break. Now I'm fine. So shall I start?
Yes, sir. Yes, sir.
Okay, thank you very much. So yes, so our another sensor is based on the glucose sensor. Okay, so I will try to cover the most of the sensor as soon as possible. So here the glucose sensor we have developed using the tapered fiber structure. So and in this we have used the nanoparticle and glucose oxidase. So here we can see the diabetes is also very common, and that creates a complication like kidney failure and diabetic retinopathy. Okay, and again this is also very harmful, especially due to the COVID. So we need to develop a sensor that you can easily detect the diabetes and level of the glucose in our human serum or human blood. So now we have also developed a sensitive, highly sensitive sensor for the glucose. So here we can see this is the kind of the simple taper fiber structure. So in that the earlier diameter was 125 micrometer and the core diameter was 8.2 micrometer. So after that we have tapered using the CMS machine and the taper diameter is 40 micrometer and the core diameter is 2.624 micrometer. So we have also cut the cross-sectional area and we have seen and we have measured the, this is quite difficult, but we have measured the cross-section part of the core of the tapered fiber section. Okay, so in this case we can try to understand how the nanoparticle immobilization occur. So as I have already discussed in the previous slide, so we have followed the three-step cleaning process and first we kept in the acetone, then in the piranha solution. The piranha solution is the combination of sulfuric acid and hydrogen peroxide, that is in the ratio of 7:3 and that produces the OH group, and after that we kept in the MPTMS. So MPTMS produces the SH group over the sensor structure, and these gold nanoparticles are attached over the SH group. Okay, so after 48 hours we have arrived with ethanol and dyed with the nitrogen gas, so that the unbounded gold nanoparticles will remove. Okay, and after that we have followed the other chemical process like MUA, ADC, NHS, and after that kept in glucose oxidase for the 12 hour for the coating of this type of the enzyme. So here the gold nanoparticles are mainly helping in the LSPR phenomena, and glucose oxidase are adding the selectivity property because this will react only with the glucose, not with the other biomolecules, and we can only we get the more variation only in the case of the desired glucose concentration or analyte. So here we can see this is the tapered fiber structure, and these gold nanoparticles are over coated over the sensor structure, and it's a UV visible spectrophotometer absorption spectrum is 519 19 nanometer, and this is the TEM image. So we have prepared the 0 millimolar to 10 millimolar concentration of the glucose, and here we can see there is a shift in the peak wavelength due to the concentration of the glucose, and we have also measured the reproducibility and reusability, and in the reproducibility we have tested the 1 millimolar concentration using the 3 different developed sensor structure and found that there is the same peak wavelength. So we can say that our lab can reproduce the similar sensor structure in the future. Okay, and we can do the commercialization. So in the reusability test, we have tested the one concentration of the glucose, and after that we have run the sensor probe, and we have detected the other same concentration again, and found that there is no peak wavelength shift, and so we can say there these sensors are reusable. Okay, and in the selectivity, this is maximum wavelength shift we got in the case of the glucose, not in the other cases, because the of the glucose oxidase that can only react with the glucose, not with the other biomolecules. So its linear range is also 0 to 10 millimolar, and sensitivity is 0.92 nanometer per millimolar. Okay. So similarly, we have also developed, we have all tried to just reduce the diameter, because if you will reduce the diameter, the more and more information will try to come outside. But there is a limitation, because we need to do some of the nanoparticles immobilization, enzyme functionalization. So we cannot go a very small diameter. So still in this case, we have fabricated 25 micrometer, and we have also used the graphene oxide along with the gold nanoparticles. So here the gold nanoparticles helps in the LSPR phenomena, and graphene oxide increases the biocompatibility nature of the sensor probe. Okay, and glucose oxidase helping in the selectivity property. So here we can see we have also shown here we can see that how in the normal region in the core and cladding the evanescent field is moving in this way, and but in the tapering section the guided field are coming outside, and the evanescent field are coming at the surrounding surfaces. So this evanescent field is helping in the sensing purpose. Okay, so here this is the BPM simulation results. So this is the experimental setup in this case, and firstly the graphene oxide, then gold nanoparticle are coated, then enzyme are coated, and after that we have done the different detection of the different concentration of the glucose. So here we have, I have already discussed about the gold nanoparticles that we have followed the modified turquoise method, and for the graphene oxide we have followed the modified hammer method. Okay, so in that we need to just graphite powder and some KMnO4, HCl, H2SO4, and some we need to do some chemical process for 2 to 3 hours, and we can synthesize the graphene oxide in our lab easily. Okay, and we can do the primary verification by measuring the absorbance spectrum. So its peak wavelength is coming around 230 nanometer and 310 nanometer. So there are two soldiers are coming on the graphene oxide absorbance spectrum. Okay, so here after coating on the optical fiber structure, we can also verify. There we can see the nanoparticles over the sensor structure, and we can also do the Acm EDS to know the exact material composition over the sensor structure. So here we can see the AU is due to the gold nanoparticle, and C carbon is due to the graphene oxide, and SiO means SiO2 that is because we have done the EDS of optical fiber structure, so that also getting the component material composition of the optical fiber structure, that is the SiO2. Okay, so we can from this EDS graph we can confirm that both nanoparticles are properly attached over the sensor structure. Okay, so we have detected the different concentration of the glucose and found that this sensor structure is quite better than the earlier sensor structure. So we have also done the stability test. In the stability test, we need to measure the different kind of different buffer solution for the different, so for the number of times, and we need to measure the peak resonance wavelength. So here the deviation is quite low, so we can say that our sensor is quite stable. And in the pH test, this is very good experiment, because in the pH test we need to prepare the glucose solution in the different pH solution. Okay, and some basic and some acidic, and other is PBS solution, that's pH is 7.4. Okay, so we have done the detection in the different kind of the lower and higher concentration of the detection in different pH values of the solution, and found that it's a maximum wavelength shift occur at the 7.4 pH. So this is also good that the pH of our human serum is also 7.4. So we can say that our proposed sensor can be developed sensor can be useful for the clinical application for the human body. So we have also tested the selectivity and found that so overall this sensor is quite better than the earlier sensor, and its sensitivity and linearity range is high. So similarly, our group has developed the sensor for the dopamine, and this work was published in IEEE Transition on Biomedical Engineering. This is also a featured issue recently. So in this case, we have used the silver nanoparticles and one kind of the material that is the PEG for the kind of the selectivity. Okay, so here we can see, and dopamine. If firstly we need to know what is the dopamine. So dopamine functions as a hormone and a neurotransmitter in the human body and plays crucial role in the peripheral system. Okay, so the abnormal level of dopamine in body leads to several disease disorders such as Parkinson, nausea, neurosis, and deficit hyperactivity disorder. So the concentration of dopamine lies in the range of 10 nanomolar to 1 micromolar in the extracellular fluid of the central nervous system. So we can see the concentration of dopamine is quite low, very low. So we need to develop such a sensor that can detect the low concentration, even the low concentration of lower or lowest concentration of dopamine in our human body. Okay, so here we can see we have developed the taper fiber using the CMS machine, and after that we have synthesized the silver nanoparticles, and we have of around 7 to 8 nanometer, and we have coated over the sensor structure. We have followed the same cleaning process, and only at the place of the gold nanoparticles we have coated the silver nanoparticles in these cases. Sorry. Yes, so we can also see this the silver nanoparticles after the coating, and we can easily verify. So in this case we have also determined the detection time, and for this case the detection time is around 25 to 30 minutes, and we have detected the different concentration of from 0 nanomolar to 100 micromolar concentration of dopamine, and we found that the selectivity range is quite high and selectivity is also very high. And as we know, the dopamine is not found alone; it's found with ascorbic acid. So we have checked the selectivity test along with the ascorbic acid and found it's also working good. So this is very good sensor. So another kind of the sensor our team has developed for the uric acid detection. Okay, so in this case we have developed the sensor using the taper fiber, and for the uric acid detection, and we have developed some 3 to 4 type of the sensor, and we have compared the sensing performance. And in that firstly we have used the gold nanoparticles, then gold and graphene oxide particles, and after that we have developed this magenta interferometer structure. This is very good structure in that we have used the single mode fiber, multi-mode fiber, single mode fiber, multi-mode fiber, and single mode fiber. So here we can see the center part of the multimode fiber is just converting the core mode into cladding mode, and after that cladding mode in the center part of the single mode fiber is helpful for the sensing purposes. Okay, and after that again combining second fiber is combining the spectrum, and we are getting output from the single mode fiber. So this work was published in the Heterodyne transition on instrumentation and measurement. So here we can see to get the more evanescent wave outside the surrounding surface, we have etched the center part of the single mode fiber. Okay, and after etching, we have coated the different kind of the silver nanoparticles, copper oxide nanoparticles, and after that uric acid enzyme to add the selectivity property. And here we can see the observance spectrum of silver nanoparticle is 395 nanometer, and for the copper oxide nanoparticle is 387. So here we can see this is the C is the silver nanoparticle and D is the copper oxide nanoparticles, and these figures E and F figures are the sensor structure after coating of the nanoparticles. So at lower magnification we can see the sensor structure, and at higher magnification we can see the nanoparticles over the sensor structure. And we have also done the Acm EDS to know that there are material composite material Ag and copper are available on the sensor structure along with the SiO2, that is along with the bar. So we have detected the different concentration of the uric acid, and we have just determined the sensing performance. So I will compare the sensing performance in later on. So recently I have also developed one more sensor that is quite good for the uric acid detection, and the sensor structure is micro ball fiber sensor structure. Okay, this work was published in Untitled Transition on Nano Bioscience. So in this case, we have developed a micro ball sensor structure of 350 micrometer. So what we can do in at the one end of the 100, we have taken the fiber of 125 micrometer, and at the one end of the 125 nano micrometer, using the fusion splicer machine, we have heated at the one end, and we have made the fiber ball structure. So we can make the desired fiber ball structure. So here the diameter of fiber ball structure is 350 micrometer is the best for the sensing purpose. Okay, so sorry. So here we can see this is something different kind of the sensor probe. So here that is not based on the transmission mode, that is based on the reflection mode. And so at the end of the fiber ball, we have coated the gold nanoparticles and graphene oxide. Here gold nanoparticle is for the LSPR, and graphene oxide to add the biocompatibility nature, and uric acid is to add the selectivity property. Okay, so here when we put the fiber ball in the uric acid, that produces the allantoin plus CO2 and H2O2. So as we can see, in the most of the biomolecules, after the reaction, their byproduct is a hydrogen peroxide, and this change in the hydrogen peroxide depends on the concentration of uric acid. Okay, so when it changes, so the surrounding reflective index, surrounding environments are changing, and due to that there is some variation in the reflected spectrum. Okay, and here we can see we are launching the light through the tungsten halogen source and getting the reflected spectrum from the spectrometer into the computer. So we have measured the reflection instead of the reflectance instead of the transmission. So here we have used the gold nanoparticle and graphene oxide. We can see the Jarvis spectrum and the TEM image. So in the first structure is based on the gold nanoparticles, and second structure is based on the gold nanoparticles and graphene oxide. Because here we want to compare that really what happened due to the graphene oxide, is there any advantage or not. So we have also shown the EDS diagram. You can see in the first diagram there is no carbon. Okay, in the second diagram there is a carbon. Means in second image is with the graphene oxide. Okay, first one is only with the gold nanoparticles. Okay, so we have measured the different concentration of the uric acid and plotted the reflectance. So we found that there is some linear relation. Okay, and after that we have also tested the sensor probe in the serum. Serum is that is normally we have collected from the nearby clinic that is associated with the university. So we need to in the blood we need to centrifuge the blood, and we need to take the upper part of the yellow color, that is nothing but that is the serum. Okay, and we have determined the concentration of 5 different serum from our proposed sensor, and we have also determined the concentration of those uric acid through the A5800 automatic biochemical analyzer machine that is available in the clinic, and found that is the comparable same. So we can say that our proposed sensor is useful for the clinical applications. Okay, so we have compared the different type of the uric acid sensors and found that some sensors are better for the that depends on the structure, and some are also for the blood, some are also for the uric acid, urine. So that depends on the applications. We can use the several different kind of this sensor structure. Okay, so we have also developed a sensor for the ascorbic acid detection, that is for the vitamin C. So in this structure we can see we have used the photosensitive fiber, and at the end of the photosensitive fiber we have etched, and due to the etching its core is made up of the highly germanium doped. So that expanded due to the etching process. Okay, so that is also called a etched expanded core. Okay, so here we can see this sensor structure is made up of the by splicing of single mode fiber and photosensitive fiber. So after that we have expanded. Its initial core diameter was 4.2 micrometer, but due to the etching it became 32 micrometers. Okay, so and we have measured the reflectance in this case, and we have determined use the ascorbate oxidase enzyme to hide the selectivity property of the sensor probe. So this sensor is quite stable, and this is a very important structure. We have fabricated a special kind of the sensor structure, that is the multi-tapered structure. So in that multi-tapered structure, first we have developed the 4-tapered, and then 5-tapered and 8-tapered, and we have compared the sensing performance of all 3 structure to detect the ascorbic acid, and we have done the coating of gold nanoparticles and graphene oxide in this case, and we can see this is the 4-tapered and 5-tapered and 8-tapered. We can. It was very difficult to take this image, but we did it, and we are able to see that last one is broken due to the length of limitation. So its magnification is smallest 111x. Okay, so taper 1, taper 2, taper 3, taper 4, up to taper 8. So, and after that, this structure is coating of gold nanoparticle and graphene oxide coated on gold nanoparticle structure. So, that is material confirmed through the Acm ADX plot. So, we have determined, we have detected the different concentration using the all three developed sensor, and we can see in the 8 tapered structure due to the multiple tapering section, the light is not guided. The most of the light, even we can see most of the light are coming in the form of radiation, and we are not able to get the light at the transmission section or transmitted part. So we can see that 8 taper was not good. Even we have compared the sensing performance and found that in the case of this 4, and we have also compared. Here we can see, and the 5 tapered structure sensitivity was 8.3 nanometer per millimolar. That is better than the 4 tapered structure and 8 tapered structure. So we have also developed a sensor for the L16. L16, that is a biomolecule found in the urine. Okay, for this we have developed a sensor structure that is based on the magnetic interferometer. This is the simple and very economical sensor structure that is made up of the single mode fiber, multi-mode fiber, and single mode fiber. So here we can see in the center part of that we have used the multi-mode fiber. Okay, so due to the core mismatch, some part of light goes to core mode goes to the cladding mode, and the center part is east, so that cladding mode will come outside as a evanescent wave. Okay, and that will be helpful in the sensing purpose. Okay, so for that we have done some different kind of the nanomaterials, and you use the structure. In another, we have developed one more sensor for the L16, and in that we have used the SMS structure. So this is very good structure because firstly we have spliced the single mode fiber, multi-mode fiber, and single mode fiber. Okay, and after spliced, we have tapered the center part of the fiber. So here, the core mismatch property and the tapering property, both property are working together, and so that's why that is more helpful in the and increasing the sensitivity of the sensor probe. So here we can see. Then our group has also developed a sensor for the collagen sensor, collagen collagen 4 biomolecules. So here this structure is like a MSM structure, a multi-mode, single mode, multi-mode structure. So in that we can see when we will send the light to the multi-mode fiber, some part of the light will go to the center core of the fiber. Okay, but most of the part of the core mode will go as a cladding mode of the center fiber. Okay, and that will be helpful in the sensing purpose. So here we can see what is the collagen. So collagen is one of the most abundant protein that is observed in the form of elongated fibrils in connecting tissue and internal organs of the mammals. Okay, so in this study, collagen 4 is the point of interest that is present in the basement of membrane. The accumulation of collagen 4 leads to several serious disorders such as scleroderma, keloids, or tumor growth and glaucoma. Means due to these biomolecules, some skin related disease can occur. And so that we need to measure the concentration of this kind of the biomolecules to avoid the skin disease. Okay, so our team has developed one more collagen sensor using the special sensor structure, that is the single mode fiber, multi-mode fiber. The center part, they use the photosensitive fiber of the 3 centimeter, and that core diameter is quite low, 4.2 micrometer, even lower than the conventional single mode fiber, and use this sensor structure. This structure is normally working as a magenta interferometer structure, and for the sensing purposes. Okay, so yes. So recently, our team has developed in last year one sensor for detection of water pollutant. Okay, that is the peak result detection based on the gold and Zinc nanoparticles modified on the taper optical fiber structure. So that is also very good, and even that can detect the peak result and from the human body, as well as also can detect from the some other water from the bad water, and we can see. Yeah, so in the second part of the work, I'm going to discuss about the microorganism detection. Okay, so in this microorganism detection, first one is I want to cover about the cancer cell detection. Okay, so this work was very quite good, and I will discuss the two work, that is the cancer cell detection, and one is bacteria detection in next 15 to 20 minutes. And these two works are very highly suitable work. In last 1 year, both work are cited around more than 30 to 40 times as per the Google Scholar. So this work was done by our team, and along with the collaboration with IIT Bhubaneswar and IIT Roorkee, and published in Biosensor and Bioelectronics. That's impact factor is right now 10.618. So here we have developed the sensor probe using the single mode fiber and multi-core fiber. Okay, and we have used the 3 nanoparticles like gold nanoparticle to add the LSPR phenomena, and gold graphene oxide and copper oxide nanoflower to add the biocompatibility of the sensor probe, and 2-deoxy-D-glucose 2DG used for the particular specific detection of the cancer cells. Okay, so here we can see this one is the fabrication process. In that we have fabricated the 2 different kind of the single mode fiber and multi-core fiber structure using the special kind of the fusion splicer machine, and after that we have cut the 1 centimeter centimeter or desired length of the fiber of the multi-core fiber, and we have etched the multi-core fiber, and after etching we have coated the different, firstly graphene oxide, then gold nanoparticle, then copper oxide nanoflower, then 2-deoxy-glucose enzyme for the selectivity property, and used this type of the setup. And in this case we have measured the absorbance variation occurred due to the variation in the analyte. Okay, so here we can see due to the etching, this is the original sensor fiber, and due to the etching, it's core diameter is expanded and the cladding diameter is also reducing. Okay, so you can see that is variation due to the 0 minute, 6 minute, 10 minute, and 15 minute. So in this case, we have used the 10 minute etching time, and we have also have synthesized the 4 different kind of the gold nanoparticles, and of the diameter 10, 30, 45, and 70 nanometer, which peak absorbance wavelength is the different. Okay, as I told that the resonance wavelength, SPR resonance wavelength, will be a different for the different diameter. So we have also measured the all nanoparticles using the HRTEM, and we have shown this picture in the picture 6. Here we can see 10 scaling is 10, 100, 102 micrometer. That's why its size is looking different. But we have measured the size and we have plotted the histogram, and found that the first one is 10, then 30, then 45, and 70 nanometer. So as I have discussed, we have followed the modified Hammer method for the synthesis of graphene oxide, and for the copper oxide nanoflower. This is very unique type of the nanoparticle. So in this, we have used the copper nitrate, and we have followed some of the chemical process. And if anyone are interested, you can refer my paper. Otherwise, you can consult me. So this is very unique kind of the nanoparticle, that is the copper oxide nanoflower, and we have done the characterization. So we have also done the TM EDS of the all 3 kind of the nanomaterial to verify that the first one is the gold, second one is the graphene, and third one is the copper. Okay, so after that, here we can see I already discussed the coating process. So after coating, we have done the Acm analysis, and to capture the all nanomaterial coated over the sensor structure. So here we have developed the 2 kind of sensor structure. First one is the non-etched structure, and second one is etched structure, to know about the impact of the etching on the sensing performance. So here we can see this is the etched structure, and here we can see its diameter is also reduces from 125 micrometer to 100 micrometer, and its core diameter is expanded from 6.1 micrometer to 20 micrometer. Okay, so and these nanomaterials we have also done the Acm EDS, and we verified that the gold, copper, and graphene oxide are presented over the sensor probe. Okay, along with the SiO2 material, that is along with the fiber. Okay, so firstly, we have done another kind of the testing by introducing the glucose oxidase over the sensor structure, and to know that which kind of the gold nanoparticle is better for the sensing. Okay, so here we have tested the different kind of the glucose, and found that in the case of the 10 nanometer gold nanoparticle, there are wide variations of wide absorbance changes. So we found that this kind of the gold nanoparticle is better for the sensing purposes. So after fabrication of the sensor process, sensor, we went for the biological experiment, and we did the cell culture. We have used the highly developed the cell culture lab, and in that we have grown the because we need to maintain purity, otherwise there will be a highly chances of the contamination. So we have developed 6 cell line and 4 cancer cell lines and 2 normal cell lines, like liver cell, liver cancer cell, breast cancer cell, pancreas cancer cell. Okay, so we have developed it. So in that we need to give the some of the media, like so in that we can also call a DEM EM supplemented with 10% FPS and 1% antibiotic to grow the this kind of the cells. Okay, and for HEP PA16, this is the different kind of the cancer cell. So for this, we need to give only 10% FPS, no antibiotic. Okay, DMEM supplemented with 10%. So we need to grow these cancer cells in the incubator. Okay, so for in incubator, we need to maintain the 37-degree temperature and as well as 5% of the CO2. We need to provide continuously, so to for the healthy growth of the cells. So after the growth, we need to we can count, we can click the some concentration, original concentration, and we can count through the henocytometer and microscope, and after that we need to do some multiplication process and all these things, and after the simple process we can determine the complete concentration. Okay, so after that we can dilute those concentration in the desired concentration. So we have diluted in from 100 cells to 10 lakh cells per ml. Okay, and we have prepared the 1 ml solutions, although we need very small quantity for the measurement. Okay, but the concentration was like this 100 cells per ml. Okay, so in this case we have kept 1 ml complete solution, so that 100 cells will just accumulate over the sensor probe. Okay, so so firstly, to determine the detection time, we have taken the one cell line of the different concentrations and detected up to 1 hour. Okay, even more than 1 hour, and found that approximate 60 minutes, its absorbance is saturated for the all kind of the cancer cells. So we found that the detection time for this kind of the cell is 1 hour. So similarly, we have detected the other cell lines and we have compared the absorbance spectrum. So that will help to separate the cancerous cell lines and normal cell lines. Okay, so even we can we have also detected the different concentration of the cancerous cell lines and normal cell lines using the non-etched and etched sensor probe, and found that in the case of the etched sensor probe, there are more observance variations than the non-etched sensor probe. So we have done the all detection, and we have also plotted the linear plot. Okay, and in that in this linear plot we found that the linear range of our sensor is 100 to 10 lakh cells per ml. Okay, so we have done some other experiments to determine the reusability and selectivity property, and we found that it's quite good. Okay, so here we can see we have also compared the proposed sensor using the existing sensor and found that the linear range is quite good than the other sensors, and as well as the limit of detection, it means is quite good. Even 2 cells per ml can detect through our sensor. So this is very good sensor than the earlier sensors. So okay, so similarly in another work we have developed a sensor using for the Shigella bacteria. So Shigella bacteria is responsible for the diarrhea in the human body. So I will finish this task quickly in 5 minutes. So in this case, we have developed some special kind of the structure, and we have used the molybdenum disulfide nanoparticle that is quite better for the biological sensing, and used the IPA probe for the specific detection of the bacteria. Okay, and we have followed some specific protocol to culture the bacteria, this kind of the Shigella sonoi bacteria, and we have followed the autoclave and all these things, and then we have diluted in the some lower concentration and detected through our proposed sensor. So good thing is that this is useful for the common society and for day-to-day application. So yes. So we have determined the different kind of the bacteria, and it's a detection time of this sensor is 5 minutes. So within 5 minutes, we can determine the Shigella bacteria even from the water or even from the human serum or blood. And its a limit of detection limit is around 2 CFU. CFU means colony forming unit. Here we can see these are the bacteria, and here we even one bacteria we can see through the naked eye, but the normally bacteria found in the form of colony. So a colony of bacteria we can able to see. So these are the colony of the bacteria. Okay, so our sensor can sense even 2 colony forming unit, meaning from any kind of the solution. So this is the advantage of our sensor. So our team has completed many health monitoring system based projects until now, and we are also doing some of the projects, and especially for the development of some more specialized sensor for the bacillary dysentery or diarrhea. So yes, and our group has published very high impact journals in last 2 to 3 years, and in last year December we have also published one book that is the 2D material for surface plasmon resonance based sensor with Professor Sanjeev Kumar Raghuvanshi. He will also give I think he is going to give a talk in afternoon. That will be very interesting for that will be on the surface plasmon resonance based sensor for the some chemical sensing and gas sensing. So I request to the audience to please listen his talk, and that will be very interesting, and he has a very good experimental facility in his lab. So if anyone want, he can collaborate, and he can go to his lab and he can do the experiment. But the candidates should have some depth knowledge so that they can do the experiment quickly. Okay. So we are also writing one more book this year, that is the optical fiber based plasmonic biosensor test technique and application under the CRC press. So we have a very strong national and international collaboration, and from IIT Roorkee, IIT Bhubaneswar, IIT ISM Dhanbad, IST Trivandrum, MIT Gorakhpur, MS Ramaiah Bangalore, and in international university Fabrio, Northumbria University, Laucheng University, and nearby hospital, and Juhai Surgapkar University. So if anyone would like to do it's a similar area, work in the similar area, and so they are most welcome, and I am always ready for a good collaboration, a strong collaboration. And I can show that in the last 2 2 years, our group has published more than 20 high impact CI journals, biosensor, bioelectronics, two paper in even biosensor in bioelectronics, that's impact factor is 10.61, and many papers in IEEE, JLT, IEEE transition on biomedical engineering, IEEE transition on instrumentation measurement, IEEE transition on nanotechnology, IEEE journal on quantum electronics, IEEE transition on nanobioscience, IEEE sensor journals, and plasma science, electron devices. So if anyone would like to do collaboration, please you can drop me an email. I'm always ready for the strong collaborative work. So these are the some of the papers that is published in collaboration. So yes, so thank you very much to listen my talk. So hope I am able to finish my presentation on time. Yes. Dr. Mandal.
Thank you, sir,
Thank you.
for your valuable talks. So, dear participants, so I think you have so many doubts. So please ask. Feel free. You can ask to our professor, Dr. Santosh Kumar.
Dr. Mandal, can you give me a 2 minute break?
Yes, sir. Yes, sir. Yes, sir.
You told me so many doubts, so I want to take 2 minute break. I'm coming back.
Okay, sir. Okay.
Yeah, sorry for inconvenience. Please ask.
Okay. No problem, sir. Okay, dear participants. So, if have you any queries regarding this lecture or presentation on biomedical sensor or fiber optics or plasmonic biosensor, so please ask. Or if your network is not so good strength, so you can write your question in chat box also. Okay, sir.
Yes, sir.
I have a question, sir.
Yeah, please, please, Dr. Mandal.
So, actually, sir, my research field is on microwave engineering, so antenna design basically.
Okay.
So, sir, how can we collaborate with you to design your sensor by using microfield?
This is very good question. Even similar type of discussion we are also doing one of my batchmate, and we are trying to develop some optical antenna. Okay,
Yes, sir.
so we can think about that to do for the optical antenna, and we can also think about the some biosensing application, even through the some micro wave range type of the antenna. Even we can see, you can see. Uh, I have handled many papers in IEEE Sensor Journal. In that, people have developed some kind of the microwave antenna, and they have done some sensing. Sensing, I mean, sensing application in the not only for the microwave communication, some of the physical sensing, some of the biological sensing they have done. So we can plan for such type of the work. If you want, we can do the separate discussion, and we can do such type of the collaborative work in the future, sir.
Yes, sir. Also, sir, different type of array antenna we are using for biomedical application to
Yes.
detect the tumors or
Yes,
different
yes.
cells.
You are right. You are
So,
right.
yes, sir. So I am, sir, very much interested to work with you, sir.
Sir, thank you. It will be my pleasure. It will be my pleasure. So of course we will discuss these things in the
Okay,
after completion of this FTP program.
okay, sir. I will discuss with you, sir.
So thank you very much, sir.
Okay, sir. Actually, sir, you are working, sir. Team endurance. This is the teamwork, sir. It is no fight, sir.
Thank you very much.
And sir, you are delivering, sir, wonderful session with us. Different the sensor you have designed for biomedical application. That is the uric acid detection sensor. Another glucose sensor, cancer cell detection sensor, different type of sensor. Actually, from top to bottom, sir, totally sensor and sensor.
So, yes.
Hello, sir.
Yes. So thank you very much, sir.
Hello, sir. Hello.
Yes. Please ask.
Sir, in maximum cases, I see that gold nanos, particularly on graphene oxides, are used for the biosensors.
No, we have used we have for the LSPR. I already told that our proposed sensor are based on the LSPR phenomena. So for that, firstly the silver nanoparticle and gold nanoparticles. These two things, either any one of these metal are compulsory. Apart from that, we have also used the graphene and some zinc oxide nanoparticle, copper oxide nanoparticle, copper oxide nanoflower, molybdenum disulfide, and currently we are using the magazine and multi-walled carbon nanotube. So we are exploring the all other nanomaterials in the coming semesters.
Among from that, which commercially which will be less cost? Among from the particles we are using, which will be less cost? Means commercially we can say that less cost.
Okay, less cost. So if you, it will be better to synthesize by yourself. So if you will synthesize by yourself, in that case, the gold nanoparticle and the graphene oxide will be very cheaper. Okay, even for the graphene oxide, if you synthesize one time, and that you can use it in the more than 20 to 50, 20 to 30 experiment. So that will be very cheaper in that case. And even those chemicals are also not very expensive. Even gold precursor is also not very expensive. It seems that it is gold, but gold is costly. But if for the synthesis of gold nanoparticles, we need a chloroauric acid, and that chloroauric acid you can use it for the long time in so many times, so that will be very cheaper, so that you can use these two materials.
Okay, sir. Thank you, sir.
Hello, sir.
Yes,
Hello, sir.
yes, please ask.
Sir, thank you for the wonderful session, sir. I don't have a doubt, but sir, it will be very helpful if you could share the slides, sir.
Sure, no problem. I will
Thank you, sir.
share my slide to Dr. Mandal, and he will share to the
Yes, sir. Yes, sir.
all participants.
Yes, sir. Thank you, sir.
Thank you.
Thank you, sir. Nice session, sir.
Thank you.
Okay, dear participants, after collecting from our experts, so I will share with all the participants. So once again, sir, thank you very much for your active participation, sir. Active participation with us.
Yes, as I told you in morning, I was supposed to cancel, but as I did the commitment with you,
Sir, it's our pleasure, sir. You are right. You are right now. You are COVID positive, also, sir. You are not canceling our session, sir. It's our pleasure, sir.
Thank you, thank you,
Praying for the speed recovery, sir.
thank you very much, and thank you, sir, and also thanks to Ashish Ranjan sir and all head of the department and director, sir. Thank you to all participants. Namaste.
Sir, if possible, sir, please come to NIT Manipur, sir.
Sure, sir. Thank you very much for invitation, sir. Thank you, sir.
Okay, sir. Thank you all.
Thank you, sir. Bye.
Okay, sir. So, dear participants, we will be back after a short break. At next session will start at 2:30 p.m.
Okay, sir.
Extrusion. Right. சௌமியா மேம், அப்புறம் ஜெயந்தி மேம், கோமதி மேம், அப்புறம் ஸ்னிருஜா மேம், அப்புறம் சரண்யா மேம், அப்புறம் கீதா மேம். ஸோ 10 பேர் போன டைம் காமிச்சிருங்க. இந்த 9 பேர் காமிச்சா போதும்.
रिटर्न भी करा ले तो रिटर्न निकाल लेंगे, उनको ऐसा लगता है रिटर्न निकाल लेंगे। नहीं, हमारे पास अलग तरह का ये है, तो मेरे पास बहुत गेट उट करते तो मतलब ये बहुत बना हुआ है कि सब तक चीजें वैसे बता दिए। मजाक कर रहा, झूठ बोल रहा। तो पुराने वाला कैसे हो गया? लेटेंट भी डाला है आज तक आईटी के में करने का सीधे वाला में 2 साल से मुझे पैसा दे दिया था, 3 साल से आज रिसर्च से ये कंप्लीट ओके मतलब चार्जिंग अपलोड करना है वो नहीं किया मतलब ऐसा ही नहीं है आईटी किया ये फ्री में करने वाला था गवर्नमेंट ने यहाँ ध्यान तो जाता सब कुछ ट्रायल डिटेक्ट करवा दिया सब कुछ करा दिया अरे पैसा वो तो पीडीएफ से निकाल एक काम चलो थोड़ा ये बताओ हमको कुछ काम किस फील्ड में काम कराओगे आपको तो एक काम करते हैं देखेंगे कुछ दे दिए हाँ 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 अरे वो किया है वो देखा अभी क्या था रिचार्ज करके दे दिया खाली थ्योरी आता है पूरा नहीं आते सब कुछ नहीं ये तो कुछ नहीं है थ्योरी इतना खराब हालत है ना तो बोलेंगे नहीं कि मैंने कहा बहुत खराब चलो ठीक है चलो जज पे रहेंगे हम तो रहेंगे ही रहेंगे अभी तक सरकार अभी तक
दाखवून द्याल सर. कोणी आलं तर ते लेटर दाखवून द्याल तुमचं बस. ओके ओके सर प्लीज स्लीप. वो ब्लँकेट चाहिए सर, एखादा ब्लँकेट गद्दा कुछ एनीथिंग ठंडा गरम सर. नाही हो हरले सर, लेटर सर ब्लँकेट वगैरे कुछ. काम काम दाम करे काम.
Hello, am I audible?
गाजर कॉलेज देत आहे.
Am I audible?
Yes, sir.
Just a 5 second. So yeah, it's not bad.
गड्ढा सॅलरी. अरे ते गरम गरम जेव्हा आणते ना त्या गरम रस्सा हे पुरं भाजून निघालं असं पुरं झोपून निघालं पण असं मस्त वाटत आहे त्या तेज तेज इसमें उसके ऊपर मस्त गरम गरम चाय और उसके बाद में एक मस्त पैकी चॉकलेट.
Hello. Hello.
Yes, sir. Yes, sir.
Voice is not coming from your side. What time we will start?
Hello, sir.
Yeah.
2:30 onwards, sir. We will start. Sir.
Okay, I am waiting for.
Okay, sir. Good afternoon, all.
So in this section,
Okay, wait,
good
ma'am.
afternoon.
Good afternoon, all. So now we are starting our session 3. In this session, Dr. Professor Sanjeev Kumar Raghuswamy is waiting to deliver his lecture. Okay, ma'am, over to you.
Okay, sir. I'll continue, sir. Dr. Sanjeev Kumar Raghuvanshi received his bachelor degree in electronics and instrumentation engineering from SGSITS Indore, Madhya Pradesh, and master degree in solid state technology from Indian Institute of Technology, Kharagpur in the year 1999 and 2002 respectively. In the year 2009, he obtained his PhD degree in the field of optics from Department of Electrical Communication Engineering of Indian Institute of Science, Bangalore. He is an associate professor in Electronics Engineering Department of Indian Institute of Technology, ISM Dhanbad. He was a postdoctoral research fellow during 2014-2015 at Instrumentation and Sensor Division, School of Engineering and Mathematical Science, City University, London, Northampton Square, London. He has published more than 100 peer-reviewed and indexed international SCI journal papers in the last 10 years. He has been published 6 books on contemporary optical fiber domain. Since the last 5 years, 6 Indian patents have been filed and published. He has been sanctioned and executed several R&D projects from different central government funding agencies, including Department of Atomic Energy, Indian Space Research Organization, Council of Scientific and Industrial Research Organization, etc. He served as a reviewer of journals like IEEE Transaction on Measurement and Instrumentation, IEEE Sensor Journal, IEEE Photonics Technology Letter, IEEE Quantum Electronics, to mention a few. He is the editor, board members, and reviewers of several Indian journals. He received the Erasmus Mundus Scholarship for his postdoc study. He is a fellow of Optical Society of India, life member of IETE, senior member of IEEE USA, and the life member of International Academy of Physics Science. Over to you, sir.
Yeah, thank you very much for inviting me for this talk. Let me share my PPT and is it visual PPT?
Yes, sir.
Yes. I'm again convey my gratitude to the NIT Manipur, Imphal, Department of Electronics and Communication for inviting me for this talk, which is sponsored by, I think, AICT, ATAL Academy. And I'm also thankful for the entire team of organizing this invited talk in this emerging area of electronics and communications. So I would appreciate this title of this sponsored event, the trend of research and development of electronics and communication area. So one of the best title for this particular event will be my talk, which is based on the recent trend and advancement of optical fiber sensors for chemical and gas detections. However, Dr. Santosh has already revealed some of the outstanding work regarding this particular area. So this is a continuation of the previous talk as well, and but this will carry you some more recent topic like related to the photonics crystal fiber, MEMS, micro systems, fiber bracket, and so on. So this will be the flow of my talk. So some of the discussion which will be correlated with each other, like we will start from the optical fiber, what is the optical fiber, and optical fiber communication link, and then we will introduce optical fiber sensors. So why the optical fiber sensors are compared to the other available electronic sensors. Then I will demonstrate some of the experimental results on metal-coated etched fiber braiding sensor for fuel adulteration applications. And this sensor has been developed in our laboratory. So I will be demonstrating some different etching and coating methods in this talk. I will be demonstrating the experimental setup of sensing amplification, metal coating process, sensitivity calculation, and tabulation. Afterwards, discussion will be carried out on avenged field sensor, fiber braiding based sensor for chemical sensing. There is a recent trends on cladding modes, which is emerging of this tilted fiber braiding. So some discussion will be required on tilted fiber braiding as well, how they are using for chemical sensings, which will be demonstrated. Then modeling the optical fiber sensor for various applications, and then analyzing of circular diaphragm piezo resistive pressure sensor under different loading conditions, continuing by photonic crystal fibers. So this will be the outline of my talk. Let us start from the optical fiber. As you know that optical fiber is now deployed all over the globe, and all the nations and countries are interconnected by fiber optic communication link. So optical fiber is deployed undersea, North Atlantic to ocean, Pacific Ocean. All the oceans are underpassed by fiber optic single mode fiber link, and that's why we communicate between one place to another by using a fiber optic networks. So optical fiber has been proved to be one of the viable options for communication as well as the free space communication. So wired communication as well as a free space communications. But propagation of light in an atmosphere is somewhat impractical because of the water vapor, oxygen particles. So there is a scattering of light and some unwanted echoes are generated. But still laser-based technology are quite successful for free space communication as well. And then we will be talking about how the optical fiber capacity is tremendous as compared to the telephone wire, which is operating at microwave frequency. And as you know, the GaN bandwidth product is constant. So the bandwidth is tremendously high for the case of optical fiber communication as compared to telephonic wire. That is why this has a next generation technology. So in fact, in 1818, Alexander G. Bell photophone transmit sound waves over beam of light. So that was the beginning of this technology. And then 1930, the TV image through uncoated fiber, they are transmitted. Few years later, the image through a single glass fiber were successfully demonstrated. Then 1951, the flexible fiber scope, that is a medical for applications, has been demonstrated. And thereafter, the fiber optic technology is serving for medical science also to illuminate the organs for some surgical procedures. And then 1956, the term fiber optics used for the first time. And 1958, the first paper was published on laser and maser. And after that, there tremendous growth of fiber optic technology. And 1960, the laser was invented, as you are all aware. The 1967 new communication medium, that's a cladded fiber, we are successfully demonstrated. And during 1960, the fiber was quite lossy. It has a loss around 1000 dB per kilometer. That is why it could not be demonstrated for high-speed communications because of the loss which is associated with the fiber. But during 1970, the Corning glass fiber, New York, they were able to reduce the loss of fiber substantially until 2 dB per kilometer with the purification process of glass. So during 1970s and 80s, high quality source and detector were invented, and late 90s, 80s, losses were reduced up to 0.16 dB per kilometer. So this was the beginning of the fiber optic communication. There are several advantages of optical fiber as compared to the other medium of communication like copper wire based technology. Capacity is much wider bandwidth. That is true for the case of fiber optic communications. Crosstalk immunity. So interchannel crosstalk is very low for the case of fiber optic communications. This crosstalk arises due to the WDM system, where the multiple wavelength signals are transmitted on a single medium, and because each wavelength carry a information, there is some interchange of information from one wavelength to the another wavelength that will retroid the whole communication medium, and that will finally reduce the information capacity, blurring the signals, and recovery of the signal is very difficult in that case. Clock synchronization is the another problem which is come out due to this crosstalk phenomena. So crosstalk is substantially reduced in DWDM system, where the channel spacing in WDM is around 100 gigahertz, that is equal to the 0.1 nanometer channel spacing, ITU recommended channel spacing. So that is the reason, one of the important reason why fiber optic communication is so much successful compared to the optical, this copper wire based technology. A part of that, immunity to static interference. So there is no electromagnetic interference phenomena is there. Fiber optic technology. That is one of the main reason, because it is not susceptible to the magnetic field. It is totally immune to the magnetic field. Safety. Fiber optic cable do not carry any current, so it does not have any shock. And fiber, since fiber is a non-metallic, it's a silica-based material used in fabrication. So this is one of the safety feature which is there with fiber optic communication. However, optical fiber is quite brittle, and tensile strength is also not so good, which can be improved substantially by coating it with some polymer jacket and so on. Longer lasting, unproven. It means that deployment of fiber optic cable is a one-time investment. Thereafter, many of the years, the sustainability of fiber optic link is there. So it has a very good lifetime compared to the copper-based technology. Security. Security is one of the important feature with optical fiber systems. Security in the sense, if you encrypt the signal by some message, then decryption can be achieved only by the authenticated person, which has a decryption key. But this facility is not available with the copper-based communication or any other type of communications, which is basically not the light wave technology. So security is one of the major concern over here. Economics. I mean, signal loss, propagation loss is very low for the case of fiber optic technology. Only fewer repeaters are required because the fiber loss is too low, so that you can communicate a longer distance without much repeaters. In spite of so much advantages, there is still some disadvantage is there. So higher initial cost in installation, as I told you, this is the one-time investment. So initial installation cost is quite high, and also required a good expertise of scientists and engineers who are basically deploying this fiber under sea or under mud. Interfacing cost. So all the fiber optic communication components are quite costly compared to the microwave components. You require the routers, you require the circulators, isolators, optical source, detectors. and so many other type of the routers and waveguide arrays, which are quite costly in terms of their fabrication cost and specifications. However, the size of optical components are quite small compared to the microwave component, because the operating frequency is terahertz for the case of optical fiber technology, which will eventually reduce the size of the device. Strength. Lower tensile strength. This is one of the weakness fiber optic technology, as I told you. Fiber is quite brittle. If you bend it quite large, then fiber can break easily, and then you need to splice it. And optical network engineers is required to diagnose the problem of fiber optic networks. So identifying where is the problem, where is the fiber optic cable is cut, is quite difficult, and you required some instrument like OTDR, optical time domain reflectometer, some couple of other components, power meter and all that, to locate where the fiber is broken. Remote electric power. So of course, routers, some of the sources are required electrical power also for signal generations. More expensive to repair and maintain. Of course, more specialized optical network engineers are required to repair and maintain the optical fiber network, which is one of the major concern. And the training is required for the person who are repairing the broken optical networks, because the splicing will also carry a good amount of loss, which you need to minimize. So tools are specialized and sophisticated. So this is the one drawback in terms of high-speed communication systems. So this is the one demonstration of optical fiber link, where the input signal is basically coded. So you are modulating the input signal by external modulator. This may be your on-off modulator or some other type of modulation technique like non-return to zero, PCM, DPCM, and so on. Depending on PSK, FSK, ASK, whichever technique you want, depending on the requirement of bandwidth and other parameters, you can modulate the input optical signal externally, and then light source which coupled the fiber with the optical fiber. So single mode fiber is generally used SMF28 for fiber optic communication system. So the coupling, there is some sort of loss of coupling the laser with fiber. So you required a very good amount of FC-APC connector or some sort of lens assembly. Proper coupling of power is required, in fact. So that is also a challenge for the engineers who are setting up the fiber optic communication link. The coupling of laser power, single mode laser power with the cable, optical fiber cable. Because fiber core diameter is very small, that is around 6 micrometer, and cladding is quite large, that is 125 micrometer, and you need to couple the laser power from the source to the core, because single mode fiber basically support only one mode, single mode, that is a fundamental mode, which you need to transmit through the on-axis of the fiber. That is basically called a on-axis rays. So the ray which is transmitted through the fiber center will not strike at the core and cladding interface. So there is a minimum loss. Intermodal dispersion loss is minimum. And this is the one of the reason why SMF28 fiber is so much successful. And then the light, the coded modulated optical signal is transmitted for very long distance through the fiber optic cable. And after that, you require again a SC-APC connector to couple the output of optical signal through this fiber to the detector. So detector may be pin photo detector, a blanch photo detector, and so on, depending on the requirement which you have. So light detector is basically a receiver, and then after converting the optical signal into the electrical signal, again the signal strength is reduced substantially, which you required a electrical amplifier, electron, and then get a basic output signal. Light source may be LED or injection laser diode. So if you have a multimode fiber and you are coupling a source with multimode fiber, that is for local area network or in some building or premises, then LED can be a viable option, and LED is quite cheap also. And but LED is a non-coherent source, so it cannot be used for long distance communications. So, but it can be used for local area network. So your option will be is to use a laser, a single mode laser or DFB laser. So amount of light emitted is proportional to the driven current. Source to fiber coupler similar to a lenses less. Even the fiber laser light can be transmitted in a free space also by using some sort of connectors and some sort of lens assembly and routers, free space routers. A mechanical interface to couple the light emitted by the source into the optical fiber, then light detector, that's a fin photodiode or APD is required for this case. So fiber type, there are multiple type of fiber like plastic core and cladding, glass core with plastic claddings, glass core and glass cladding. Under research like non-silicate zinc chloride classes. So depending on the requirement, suppose you want to induce the nonlinear effect in optical fiber, then you need a highly susceptible material in the fiber like zinc chloride. So this material is used for nonlinear optics to excite some other nonlinear phenomena like four-phase mixing, self-phase modulation, cross-phase modulation, soliton wave generation, and so on. And plastic fiber has a good tensile strength, but it has a high loss. So plastic fiber cannot be used for communication systems, but it is used for some local area network and for some biomedical applications. So plastic core fiber has a very good tensile strength, good mechanical strength. They do not break. Even you twist it properly, fully, the fiber will not break at all. But silica fiber, definitely you cannot twist it. You cannot spiral it, you cannot bend it. So depending on the application, you can choose the fiber. Plastic fiber, as I told you, used for short run because of higher attenuation, but easy to install, just like pipe, better with a stand stress, less expensive and 60% less weight. These are some advantages of plastic fiber. This is a optical fiber, which you can see here. An optical fiber is a glass structure specially designed in order to efficiently guide light along its length. So step index optical fiber, which you know, light guidance by means of total internal reflection, widely used in telecommunication. In fact, strip index is single mode fiber where the refractive index discontinuity is like a step function. And multimode fibers are used for decoration applications, for illumination purposes, and so on. But strip index single mode fibers, single mode fiber are used for communication system, and light is basically guided inside the fiber core, high refractive index fiber core, by the cladding. Cladding has a slightly lower refractive index. So index difference is called a refractive index difference between core and cladding. And light is striking at the core and cladding with some angle. And this angle has to be maintained. If the incident of light is less than the critical angle, the light will be trapped inside the core of fiber. Otherwise, the light will be leak away to the cladding, and this is called the avincient wave. So in this diagram, theta c, that's a critical angle that is given. So critical angle depends on the index contrast as well as the index difference. So refractive index difference is one of the important parameter here. And of course, the numerical aperture of fiber is also play the role in the high-speed communication system and power gathering capability of fiber. So light is accepted by the fiber in the form of one conical shape. So that is called the power gathering efficiency of fiber. That also depend on the cone size, and it also depend on the angle of the ray which is entering through the fiber. So on-axis ray is basically without communicating without striking the core and cladding interface, and that is a fundamental mode, and that will be transmitting to a longer distance without any dispersion effect like in the fiber. So fiber cladding in this diagram, fiber cladding is also coated by a polymer jacket to improve its mechanical strength, so that you can bend it fiber with some radius without any damage. If you will not provide the polymer jacket, the mechanical strength of the fiber is reduced. So this is a types of optical fiber which you can see. Single mode strip index fiber. Single mode strip index fiber, basically the light is incident on the center of fiber because the fiber core radius is very small, that is 3 micrometer. So it can accept only a one single ray. So this ray is basically called a on-axis ray and transmitted through the fiber for long distance. So single mode fiber is used for long haul communication systems. Similarly, you can see here is a multimode strip index fiber. So multimode index fiber has a large core diameter that is around 60 micrometer. So fiber has a large acceptance cone. Numerical aperture of the fiber is large, and multimode strip index fiber accept a large number of rays to transmit through. Because large number of mode is supported by the multimode fiber, each modes propagate with different speed because they have a different launching angle. And these rays are reaching at the different time at the fiber end. This will create a pulse dispersion or intermodal dispersion arises, which will reduce the information capacity of fiber. That is why the multimode strip index fiber is not used for long haul communication system, but it is used for small area network, local area networks. So even though during 1970, multimode fiber we are playing a good role in sensor and communication systems of fiber optic technology, then how to reduce the intermodal and pulse dispersion in multimode fiber, this challenge was undertaken and graded index multimode fiber were developed. So graded index fiber has a refractive index profile like this. So variable refractive index profile is there in the core, and actually the refractive index is high at the center of fiber and it is gradually decreasing towards the cladding. So in that process, when the refractive index is high, the pulse will travel with slightly slower compared to the other ray which is passing through the lower refractive index medium. So eventually all these rays are reaching to the same time at the end of the fiber, and that way you can substantiate the intermodal dispersion in optical fiber, and you can increase the communication length in the medium. So there was a single mode strip index fiber which has many advantages like minimum dispersion. All rays takes same path, same time to travel down the cable, a pulse can be reproduced at the receiver very accurately. Less attenuation can run over long distance without repeaters, large bandwidth and higher information rate. What is the disadvantages of single mode strip index fiber? Difficult to couple light in and out of the tiny core. Highly directive light source is required. Interfacing module are more expensive. These are some pros and cons. Multimode strip index fiber is inexpensive, easy to couple light into fiber, result in higher signal distortion, lower transmission rate. Multimode grid index fiber is intermediate between the other two type of fiber, so that has a slightly advantage and disadvantage both are associated. As I was telling you, the fiber optic communication depends on the acceptance cone of rays. So if you see this multimode fiber, which has a certain cone shape of schematics, through which the rays which are only launching on this cone area will be accepting by this fiber. The ray which is not inside this cone will be discarded by this fiber. So the area of this cone basically decides the amount of the ray which is supported by the fiber. So some one ray is which is passing through the center of the fiber, which has a no dispersion. Some ray which is incident on the extreme angle. So these rays are striking at cutting interface and passing through with this repeated repeated total internal reflection phenomena. So acceptance angle is the maximum angle in which light rays may strike the air fiber interface and still propagate down the fiber with loss less than 10 dB. Critical angle is defined by this expression. The numerical aperture is also depends on the critical angle of fiber, and which is given by this expression. So guiding process of fiber. The fiber has a two method of guidance. One is the refraction and second is the scattering. You know the phenomena of total internal reflection as well as refraction theory. So light is basically confined in the core by total internal reflection phenomena. But the scattering is also there, of course, because of the irregularity of the fiber medium, some impurities in the fiber medium, and so on. What is the refractions? Basically, here the center core has a more effective index of refraction than the cladding. Ray is guided by total internal reflection. The fundamental mode is confined to the core due to the higher index of refraction, and it is enabled to leak away since the corresponding electromagnetic fields are not in mode. Scattering guidance process is achieved by coherent backscattering of the light into the core. Light incident upon the core cladding interface is strongly scattered by the air holes. For particular wavelengths, the scattering process results in constructive interference of the reflected ray in the core. So losses in optical fiber cables, the predominant losses in optical fiber are absorption losses due to impurities in the fiber material. Materials or relay scattering losses due to microscopic irregularity in the fiber. Chromatic or wavelength dispersion because of the use of a non-monochromatic source. Radiation losses caused by bends and kinks in the fiber. Modal dispersion or pulse spreading due to rays taking different paths down the fiber. Coupling losses caused by misalignment and imperfect surface finish. So these are some processes and some reasons for the loss that are associated with the fiber optic cable. This is the typical loss spectrum of optical fiber. where the relay scattering is predominant at the lower wavelength region around 0.1 micrometer, and there is a some kinks is there, peak is there of loss. This peaks is coming due to the hydroxyl ions absorption phenomena. So this loss profile is something like that. This is the infrared absorption. These all peaks are associated due to the improper fabrication process of fiber, and these hydroxyl ion are associated in the fiber. So recently the Alcatel-Lucent has completely removed all these peaks. That is called a all-wave fiber, and they practically remove all these losses in the fiber by recent fabrication techniques like proper deposition of gases inside the hollow core and preform fabrication techniques. Even the fiber optic cable has to be bent. It has to be spliced, two fibers, and there is a bending loss is there in the optical fiber. Fiber cable is multiple times in loop. It is tilted. It is moving around in one place to the another place with various zigzag places it is passing through. Fiber is sometimes broken, and then you need to rectify it. You need to splice the fiber. So there are various type of the misalignments is there in the fiber optic communication systems. That is axial displacement. This is due to the improper axial alignment. Gap displacement, even two fibers are spliced, still some gap has to be remain due to the improper splicing process. Angular displacement is also when you bend the fiber and you splice them, then this type of the angular displacement arises that can give you the loss of information in a communication systems. And then imperfect surface finish. If you splice a two fiber without cleaning it properly, then there will be some ruggedness which is associated in the surface, and that will also create losses in some particular circumstances. So this is the spectrum of absorption losses in optical fiber. So relay scattering and ultraviolet absorption is one of the dominant loss mechanism which has to be substantiated by the engineers. And again, the peaks are arising due to the hydroxyl ions in this spectrum, and then absorption, infrared absorption region started. So this is the loss profile of fiber, which you can see at around 1.55 micrometer, you have a minimum loss of optical fiber. That is around 0.2 dB per kilometer. Light source, as I told you, that LED, light emitting diode, is a very trivial source, cheapest source, and which is used for multimode, couple the light with multimode fiber. Some light source are used, fabricated by semiconductor technology, that is a semiconductor laser diode. They are made by aluminum, gallium arsenide or gallium arsenide phosphide materials. Light is emitted when electron and holes recombine, either surface emitting or edge emitting. There are various geometrical features are there with the laser source like a waveguide grating based laser, BFB laser, injection laser diode, and so on. So depending on the requirement, like if you want to transmit information for long distance, long haul communication system, then you need to have a DFB laser, distributed feedback back reflector laser. There is a, what is the difference between LED with ILD, injection laser diodes? So advantages of semiconductor laser diode is more focused radiation pattern, much higher radiant power, faster on-off time, higher bitrate possible, monochromatic light source, reduce the dispersion. There is some disadvantage also, like much more expensive, higher temperature, and shorter lifespan. So light detectors, One of the important parameter is the detector in optical fiber communication systems. So what is the detector? Light detectors. As I told you, pin diodes is used as a photoreactor. So what is the role of photoreactors? Photons are absorbed in the intrinsic layer. So it is basically a photon collection process. So it count the number of photon which is incident on the detectors. Sufficient energy is added to generate carriers in the depletion layer for current to flow through the device. Then much more advantageous photoreactor is a APD, avalanche photodiode. Photo-generated electrons are accelerated by a relatively large reverse voltage and collide with other atoms to produce more free electrons. So avalanche multiplication effect makes APD more sensitive but also more noisy than pin diode. Actually, in APD, there is an internal gain mechanism is there. So this APD is much more sensitive compared to the simple pin diode. So before any deployment of any optical fiber communication link, you need to have some power budget and bandwidth requirements. So I think some of you might have studied this in optical network systems, how to manage the power. So there is a margin is there. So power or loss margin has to be calculated by these expressions, where PR is the received power, dPm is the receiver sensitivity, and transmitted power, M's contingency, loss allowance, source to fiber loss, total connector splice loss, fiber to detector loss. So there is a n number of connectors which are connected with the optical fiber communication link. Then you have to consider all the losses in designing the fiber optic network systems. WDM is one of the phenomena through which you can increase the capacity of the communication systems. So WDM sends information through a single optical fiber using a light of different wavelengths simultaneously. So laser optical source has a suppose n number of wavelength components. All these wavelengths are multiplexed by this multiplexer and transmitted through this optical amplifier and fiber, and then again demultiplex in this way, and you can again recover the signal after propagating through hundreds of kilometers. So recently the WDM system is subsided by DWDM system because the scientists want to pack more number of channels in a single area. So dense wavelength division multiplexing is you can pack a more number of wavelengths. So WDM is generally accomplished at 1550 nanometer wavelength because of low dispersion, because of low attenuation of fiber at 1550 nanometer. But of course, there is some dispersion around 20 picosecond per kilometer nanometer. This dispersion can be substantiated by using a dispersion compensation fiber. So each successive wavelength is spaced around, as I told you, 100 gigahertz. ITU adopted a spacing of 0.8 nanometer or 100 gigahertz separation at 1550 nanometer for dense wavelength division multiplexing systems. WDM couplers at the demultiplexers separate the optical signal according to their wavelength. So recently, as you can read in some magazines, the WDM and DWDM is also obsolete, and people are working on mode division multiplexing axis. So instead of wavelength, scientists are using a multimode interference device to multiplex the mode, and this is again tremendously enhancing the performance of communication systems. Now, having discussed on all these fiber optic systems, now come to our next topic. This is the optical fiber sensor, which is intended to speak on that for this FDP program. So what is the optical fiber sensors? Optical fiber sensors converts light rays into an electronic signals. Optical signal sensors are a class of device that use various forms of light matter like photon atoms interaction to detect, interrogate, and quantify molecules for multiple applications. An optical sensor is composed of a light source that generates electromagnetic waves, a sensing platform in which light interaction occurs, and a detector that identify and quantify spectral shift in electromagnetic wave upon interaction with integrated analytes. Of course, the sensing principle of an optical sensor is based on shifts in characteristic optical signal of an optical platform resulting from interaction with analyte molecules, which are then translated into quantitative or qualitative measurements. New revolution of optical fiber sensor, it is a spin-off from other optical technologies, seeing the potential in sensing applications developed as its own field. So why is optical fiber sensor? Because of electromagnetic immunity, electrical isolation, compact and light, both point and distributed configurations, wide dynamic range, amenable to multiplexing. Optical sensor measurements like temperature sensor, you can design pressure, flow, liquid level, displacement, vibration, rotations, magnetic fields, and accelerations. All these type of sensors can be developed. Chemical species, that's a biological measurement, biological things, which can also be developed. Force, radiation measurement can be done. pH sensor can be developed. Humidity sensors, strength sensors, velocity sensors, electric fields, and acoustic fields. So all these type of the sensors are very successfully developed by using a fiber optic technology. So working principle of fiber optic sensors, like optical source is used, feed fiber, and that has to be passed through the measurement zone, and again coupled with the fiber, and then optical detectors. So light beam changes by the phenomena that is being measured. Light may change in its 5 optical properties like intensity, phase, polarization, wavelength, and spectral distributions. Sensing details. So intensity-based sensors, frequency varying sensors, phase modulation sensings, polarization modulating fiber sensing. So these are some sorts of phenomena which are associated with the fiber optic sensor. So suppose when you launch a white light with a grating, then diffraction grating, then depending on the interaction length of wavelength, you can get a different color of light, just like a prism. Prism is also when you incident a white light, since white light contain all the colors and all these wavelengths are experiencing a different amount of refractive index and they are traveling with different speed, they are appearing at a different pattern at the output of prism. So classification of sensors, it's extrinsic sensor. So extrinsic sensor can be built up. So light source, feed fiber, return fiber, and light detector. Where the light leaves the feed or transmitting fiber to be changed before it continues to detect by means of a return or receiving fiber. Intrinsic sensor is also can be made where the sensing phenomena is taken place inside the fiber. So when you apply a pressure on some fiber Bragg grating light, then the strain is created in the fiber surface that will eventually change the Bragg wavelength. So why don't we use this phenomena for developing a intrinsic sensor? So that is quite successful. So there is a one comparison setup here over extrinsic versus intrinsic sensor. So what is the extrinsic sensor? They are used for like temperature, pressure, liquid level, and flow measurement. Intrinsic sensor like rotation, acceleration, strain, acoustic pressure, and vibration sensor. All these were successfully demonstrated. Extrinsic is a less sensitive, easily multiplexed, increase connection problem, easier to use, less expensive. Contrary to this, intrinsic sensor is more sensitive, tougher to multiplex, reduced connections problem, more elaborate signal demodulation, more expensive. So sensor type like chemical sensors, gas sensors. So chemical sensors like remote spectroscopy, groundwater and soil contaminations, major players in chemical sensor like pharma, SIA Biotech Sweden, Fibercam, the Quantum Group. Temperature sensors like largest commercially available sensors range from minus 40 degrees centigrade to 1000 degrees centigrade. US small companies in Japan like Hitachi and Sumitomo, they are developing those things. Strain sensor is also recently demonstrated based on fiber aggregating technology, sensors as little as 9 micro strain. NRL and United Technology Research biomedical sensors is also been fluorized like spectroscopic biomedical sensors. CO2, O2 and pH can be measured simultaneously. Flow monitoring by laser Dopplerimeter. So let us come to our sensor development process in our laboratory of Department of Electronics Engineering at IIT ISM Dhanbad. So this talk is based on design and experimental analysis of metal coated edged fiber grating sensor to detect the level of fuel adulteration. The problem facing due to adulteration, as you know, this is one of the biggest and challenging problem for the worldwide, how to detect the adulteration in the fuel. Like avionic fuel is required to be highly pure. If you adulterate it, there may be some tragedy which you cannot anticipate. So what is adulterations? The action of making something poorer in quality via the addition of other substances into the main substance. Fuels are contaminated by adding an inferior quality is referred to as adulterated fuel. Problems facing because of it, one of the main reasons for increasing in greenhouse is from emission due to the adulteration of automobile fuels. Engine malfunctioning, failure of components and compromised safety are on the record as a result of adulterated fuel. Different methods adopted to detect level of adulteration, like filtration techniques. In this method, some method like this filtration techniques and titration methods and so on still existing. In this method, drop the petrol on the filter paper from the nozzle. It will evaporate in about 2 minutes without leaving a mark on the filter paper. If we notice a mark, then there is a possibility that the petrol is adulterated. This is one of the very trivial method for detecting the fuel adulteration, which is not very reliable as well as not very efficient in some circumstances where the avionic fuel we are talking about. Fractional distillation technique is also available, like in this method of fuel adulteration detection, a sample of the fuel that is being filled is heated to a temperature which is equal to the boiling point of kerosene or petrol. This is all our non-invasive methods and very tough to implement, which is not very handy methods. So we are proposing here one fiber optic sensor development for fuel adulterations. Image processing method is also available. Successful as well. A small camera is fixed inside the fuel tank, which takes the images and send it to the pre-programmed microcontroller which helps to detect the amount of adulterant. Some recent research utilized an intrinsic intensity modulated fiber optic sensor for adulteration detection in petrochemicals. The principal mechanism behind this idea was the emission wave absorption spectroscopy. Several other methods have also been employed for testing the level of kerosene in petrochemical like petrol and diesel. This was the proposed experimental setup for our etching process in the departments. So one fiber container, Teflon container has been used where FBG was dipped, and optical fiber holder they are put it up there and connected with single mode fiber to the optical interrogator. So FS22DI model has been used for our this sensor development, and it is interfaced with one laptop for monitoring the reflectance spectrum. This is the etching equations and result. This is the reflectance versus Bragg wavelength shift using an optical interrogator. That's a real-time recording has been done in our laboratory, and Bragg wavelength shift has been also experimentally observed with etching time. And FESEM has been performed to find out its width after etching of fiber. So standard FBG has a Bragg wavelength shift that is equal to 2n effective multiplied by the grating period. And during etching process, this has been changed to change of Bragg wavelength depends on the change of refractive index as well as the surrounding medium refractive index. So this was the experimental setup of our sensing systems. So monitoring system, interrogators, and vertical etching process has been demonstrated. Dip coating machine has been used, fiber holders, FBG sensor head, and sample container for this experimental setup. So coupling core mode into cladding and sensing layer, tilted fiber brigating has been also experimentally studied, and its sensitivity has been computed with respect to the cutoff wavelength, change of cutoff wavelength with respect to the change of surrounding medium refractive index. NS is the surrounding medium refractive index. So this is the unedged fiber brigating. This is the edged fiber brigating. This is the unedged cladding or cladding interface. So basically grating is working here as a scattering medium where the light is scattered from core to the cladding medium. And in that process, some power is coupled to the cladding side, core to the cladding side, and that will eventually give a tremendous amount of the sensitivity because the cladding mode is more sensitive to the outer environment like temperature, pressure, and humidity, and so on. This is the sample preparation in our laboratory. Since kerosene is miscible with petrol and diesel, we used a molecular concentration formula to prepare a desired sample. Different concentration when mixed kerosene, it then left for a few minutes to well settle throughout the volume before sensing. The concentration of adulterant were increased at the successive step of 2%, 10% to make the various solutions of adulterated petrol and diesel. Refractive index sensing is the backbone of many chemical sensors, as this is the fundamental property of nearly all the materials. Refractive index of pure petrol is 1.427, diesel 1.463, and kerosene is 1.442. Kerosene has a higher refractive index, but measured with the help of ATAL RX7 refractometer. So in order to find out all refractive index values in each level of concentration, a refractive index governing equation is used, where K is the amount of adulterant concentration mixed in percentage. So this was the calculated refractive index versus kerosene concentration in chemicals. So calculated refractive index for diesel and calculated refractive index for petrol experimentally by refractive photometry. This was the reflectance spectrum in case of adulterated diesel. So you can see pure pet diesel has a black spectrum, and 90% pure diesel has a red, 80% diesel has a blue, and this is trend is followed. So there is a substantial amount of Bragg wavelength shift as you adulterate the fuel. This is the basis of our developing the sensor in our laboratory for fuel adulterations. Similar trend has been followed for the petrol also. So black one is the pure petrol. This is just a contrary to the diesel. The spectrum is started from here and it is keep on shifting to the right hand side. But for the case of pure diesel, it is shifting towards the left hand side as you increase the adulteration. So a Bragg wavelength shift is quite very sensitive for the change of any analyte. So another another method which we have adopted for developing a norm sensor is a metal coating process onto electron EFBG sensor head, etched FBG sensor head. So titanium oxide metal is uniformly coated using E-beam gun based on plasma PVD techniques, plasma vapor deposition techniques. This metal is used to enhance the optical properties near infrared region. The allowed coating thickness is 35 nanometer uniformly. X-ray diffraction has also done to describe the surface morphology of sensor head. So this is the experimental result of sensitivity calculation. So etched FBG and titanium coated FBG, etched FBG, both has been plotted with respect to the refractive index, and their linear fit means their interpolation polynomial representation along with their recreation parameter has been reported, and for kerosene concentration in diesel and kerosene concentration in petrol. So their polynomial, first order polynomial has been proposed, and their regression parameter has been set up, and they have a around 99.74% correlation factor with the kerosene, with the petrol. But in case of diesel, it is around 98.5% correlation factor. But they are quite resembled. I mean, etched FBG and titanium oxide coated FBG demonstrate a different amount of Bragg wavelength shift with respect to the concentration of fuel. This is the basic of our developing the sensor in our laboratory. So reported sensitivity is type of fiber like etched fiber Bragg gating. So 17 micrometer core diameter remain intact during the etching process, and sensitivity has been computed with respect to the percentage of adulteration. So diesel, for the case of diesel, it was a 5.7 picometer per 1% adulteration, and for the case of petrol, it was 7.61 picometer Bragg wavelength shift with respect to 1% adulteration. This sensitivity has been computed in terms of nanometer per refractive index unit. So for the case of petrol, it was coming out to be 49.98 nanometer per refractive index unit. And for the diesel, it was coming 26.97 nanometer per refractive index unit. For the case of titanium oxide coated etched fiber Bragg grating, the sensitivity has been computed for the case of petrol, that was coming out to be 54.98 nanometer per refractive index unit, and for the case of diesel, it was coming around 32.25 nanometer per refractive index unit. So analyzing of titanium oxide coating, in fact, the titanium oxide has a higher refractive index compared to the silica cladding. So this total internal reflection phenomena is completely reversed. So this Poynting vector direction is reversed basically. This is the one of the pluggative phenomena which is responsible for increasing the sensitivity of titanium coated edged fiber bracketing compared to the simple edged fiber bracketing. So after metal coating, the same procedure is followed by sample preparation, and 4 repeated set of testing adulterations are performed. The higher refractive index of titanium oxide than silica deposited onto the edged cladding induced field confinement and enhancement in the interface between cladding and titanium oxide, resulted in enhanced sensing ability of the edged FBG based sensor. Titanium oxide allowed the increment in sensitivity around 19.57% and 10.1% EFBG based sensor in diesel and petrol respectively. We present a single mode fiber titanium oxide coated edged fiber bracketing based sensor for the determination of adulteration and petrochemicals. The Bragg wavelength change in response to change in surrounding refractive index is measured. The sensitivity of 26.97 nanometer per refractive index unit and 49.98 nanometer per RIU were estimated in diesel and petrol respectively, with 17 micrometer diameter of the cladding. Furthermore, titanium oxide coated EFBG given the sensitivity of 32.25 nanometer per RIU and 54.98 nanometer per RIU, that is enhanced by 19.17% and 10.1 in diesel and petrol respectively. Due to real-time on-road measurement benefit of this proposed sensor, it would be very useful for the petrochemical and automotive industries. Also, this sensor exhibits robustness and inflammable to the surrounding hazardous substance. Therefore, it helps to improve the engine life and healthy environment. Next phase of our discussion today is the development of fiber bracketing based Evansient field sensor for chemical sensing. So FBG assisted chemical sensor is one of the technological advancement in this last 2 decades. So couple core mode into cladding and surrounding medium. Of course, a radiation mode will come in a contact with analyte around fiber and monitor the shift of the Bragg wavelength change with surrounding medium refractive index. So as you etch the fiber bracketing, you basically increase the chance of field to decay from core to the cladding and cladding to the surrounding medium. So interaction with the analyte is much easier for the edged fiber bracketing. This is one of the basis for developing the FBG based Evansient field sensor. Another area of investigation is tilted fiber bracketing, where light is basically scattered from the tilted FBG from core to the cladding and cladding to the analyte. And this process is very important for developing a very highly sensitive grating assisted surface plasmon sensors as well. So here you can see in this diagram that incident light is striking on this high-low refractive index medium, where the refractive index is tilted plane. So tilt angle and grating period is also has this relation. This is the normal grating period and this is the tilted fiber bracketing period. So tilted fiber bracketing has a low grating period that will eventually affect the Bragg shift. This is the tilt angle, grating tilt angle, and this is the total grating length. And these are the cladding modes which is arising after this striking of O to the periodic refractive index medium. So if you simulate this, then transmittance versus wavelength spectrum you can get like that. This is not usual fiber grating transmittance spectrum. This is like a some different type of appearance, like home type of filtering action is there. This is basically a core mode. This is the near 1.56 micrometer wavelength, and these are plenty of the cladding modes are emerging out, and these are the lower order cladding mode. These are the higher order cladding mode, and this is called the ghost mode. This outer cladding mode is highly susceptible for the analyte refractive index. So you can basically develop a very good sensor based on the tilted fiber grating. So how does the cladding mode vary with change in grating parameters? In this simulation, the transmittance spectrum of tilted fiber grating has been computed with respect to the grating periods and angle of incident as well. And this is the basis of our developing a tilted fiber grating based sensor. H5 grating sensor, which we recently developed in our laboratory, has a two strategies. One is RGO coated H2 FBG for salinity sensor. So reduced graphene oxide coated H2 fiber grating sensor for salinity sensor development, and slightly etched, means partially etched, coated FBG, titanium oxide coated etched FBG for glycerine sensing. So basic sensing principle is like that. The refractive index, effective refractive index of FBG changes with respect to the refractive index of solution, that's analyte refractive index. And in the y-axis right hand side, this is the Bragg wavelength shift at different cladding radius. And this is the reflectance, experimentally obtained the reflectance spectrum for etched and unetched FBG. And there is a observation of blue shift and red shift as you etched the cladding slightly. And this phenomena is used in our sensor development. This is our experimental demonstration at the departmental laboratory. So fabrication and experimental analysis of reduced graphene oxide coated etched fiber grating refractometric sensor is demonstrated here, where optical interrogator, bait machines, this is the etching process, and this is the graphical user interface. So horizontal etching and vertical etching both has been adopted. This is the vertical etching process shown in this diagram, where this interrogator is connected with this graphical user interface software to the monitoring system, and this diagram shows the Teflon container for holding the HF acid. So this is basically the demonstration of etching process in our departments. And reflection spectrum has been experimentally obtained for the RGO coated FBG at various times. So there is a Bragg wavelength shift, blue shift, red shift is arising. So Bragg wavelength shift versus etching time is demonstrated in this diagram B, where this is called the red shift and this is called the blue shift. Blue shift arises when the cladding is almost partially removed. So you have to stop the etching process, otherwise whole fiber Bragg grating will be broken. So there is a real-time monitoring of etching process. That facility we have developed in the department, and there were observed a 0.25 nanometer of overall blue shift in Bragg wavelength, and rate of red shift was 0.071 nanometer per minute initially, and accelerated up to a maximum of 0.305 nanometer per minute with ultimate blue shift. This is the microscopic images of different conditions of fiber Bragg grating. Transition of etched FBG, etched fiber Bragg grating, and RGO, reduced graphene oxide coated FBG. This is the algorithmic process of showing the experimental analysis of titanium oxide coated EFBG sensor for sensing. So this is the experimental setup of our departments, and this is the flow chart of the complete procedure for single measurement. So splicing and etching of single mode fiber, titanium oxide coating using E-beam gun system, interface interrogator with computer, take reference Bragg wavelength, put sample in glass beaker and dip sensor head using a dipping apparatus, prepare different samples of glycerin solutions, and then wait for stable data. Record shift in Bragg wavelength, lift fiber with the help of dipping system, box the fiber sensor head with isopropanol and deionized butter, dry sensor head, and then Bragg wavelength shift to original position, continue to be observed, then sensor head ready for another sample. So this work our published in some IEEE transaction journals. So this was the sensor performance, which is observed in real-time monitoring system. So power decreased due to the absorption of glycerin, the reflectance intensity versus refractive index is computed here. This is some more analysis of etched and coated FBG, where the Bragg wavelength shift is shown. So sensitivity has been computed in nanometer per refractive index unit versus refractive index. And this diagram shows the Bragg wavelength shift of etched fiber bracketing and their polynomial representation, titanium oxide coated etched fiber bracketing and its polynomial representation. And this is the value of regression coefficient used for fitting experimental data obtained with polynomial described in. This is the summary of our this real-time monitoring of sensor. Tilted fiber bracketing sensor protocol regression analysis to correlate sensitivity and grading parameters, parameter optimization for high sensitivity, and then experimental analysis and validation. Sensitivity computed in this case is 348.6 nanometer per RIU. Then EFBG sensor were developed by us, that is etched fiber bracketing sensor. So experimental work is being carried out for RGO coated salinity sensor. Then sensitivity computed by was 3.99 nanometer per refractive index unit. Then titanium oxide glycerin sensor were developed. That sensitivity was computed 11.9 nanometer per RIU. This is a summary of our various type of the sensor development in our department. So only etched FBG sensor. We have sensing chemical was saline solution. Sensitivity computed to be 1.7 nanometer per RIU in the dynamic range of 1.33 to 1.38 refractive index unit. Then RGO coated FBG sensor were developed with saline solution. So sensitivity was computed to be 3.99 nanometer per RIU. That is in refractive index range of 1.33 to 1.38 RIU. Slightly etched titanium oxide coated FBG glycerin water solution is used as a chemical. Computed sensitivity was 11.9 nanometer per RIU. And then fourth sensor tilted fiber bracketing analyzed with glycerin water solution with sensitivity around 348.68 nanometer per RIU in 1.39 to 1.47 RIU dynamic range. Having said this, let me discuss a little bit about a MEMS based optical fiber sensor for various applications. So micro electromechanical system, as you know, micro optomechanical system is one of the biggest market nowadays, and that is the next generation sensing system as well. So basically the materials used for MEMS is silicon, polymer and metals. Silicon as a substrate material, which is a pure, cheap and well characterized material, available in abundance. Processing techniques is easily accessible. Potential for integration and reliability is also very high. So there are various ways through the MEMS sensor are fabricated, like bulk micro machining. And you are aware that nowadays there is a good compatibility of silicon material with fiber optic material. Like you can build a laser along with microelectronic component on the same substrate. So there is a very good compatibility of materials with the microelectronics component fabrication along with fiber optic component fabrication. So bulk micro machining is basically this fabrication technique builds a mechanical elements starting with a silicon wafer and then etching away unwanted parts, leaving behind the desired mechanical. So first silicon material substrate is taken, and then ion implantation like boron creates a p-type film at surface, and then back sputtering, back patterning hole is opened at the back with lithography or etching process, and then etching the wafer whole thickness in hydrochloride KOH solution. This etching stopped at the p-type layer do etch rate, creating a membrane that is used in MEMS. So bulk micro machining fabrication for capacitive pressure sensor. The wafer is photo pattern which leaves a protective layer on part of the wafer. Wafer is then submerged in the liquid etchants like potassium hydroxide, which eats away any exposed silicon. There is a bulk micro machining and surface micro machining. So surface micro machining is a different mechanism. Surface micro machining builds a device up from wafer layer by layer. It is a repetitive sequence of depositing thin film on a wafer, photo patterning the film and then etching the pattern into the films. These layers are alternating thin films of a structural material and a sacrificial material. The structural material forms the mechanical element and the sacrificial material creates the gap and space between the mechanical elements. At the end of process, the sacrificial material is removed and the structural element is left free to move and function. So this is a complete flow diagram for this micro cantilever using a surface micro machining techniques. This is the complete process of fabricating a micro machining MEMS micro cantilever systems. LISA is when also relies on lithographic patterning, but instead of ultraviolet light streaming through a photolithographic mask, this process utilizes high energy X-rays that penetrate several hundred microns into thick layer of polymers. The exposed area are stripped away with a developing chemical, leaving behind a template which may be either a structural element or the master for molding process. So this is a LISA process which is demonstrated here. Then come to the pressure sensor. The pressure is applied on sensing element and the physical movement will take place because of deflection of diaphragm, and then transduction mechanism which convert this physical movement into the electrical signal. So pressure measurement can be done for very high value like megapascal, gigapascal by this MEMS pressure sensor. So MEMS, this pressure sensor has a categories like piezoresistive, capacitive and piezoelectric. So piezoresistive pressure sensor is like that in this diagram. MEMS piezoresistive pressure sensor. When a uniform pressure is applied, silicon micro diaphragm reflection occurs and internal strain of the diaphragm changes. So silicon is a piezoresistive material such that its resistance changes when the internal strain varies. If the pressure sensing resistors are placed on top of the thin diaphragm, pressure can be measured by monitoring the resistance change. So there is a diagram of metal conductors, silicon substrate, silicon diaphragms, bond pad, p-type piezoresistor. So there are various mechanisms there. Then capacitor pressure sensor, the sensor relies upon the applied pressure which alters the distance between the two electrodes, resulting in a change of capacitance. Typically, one electrode is fixed and another is movable. Both the electrodes are separated by a small gap which allow a membrane deflection. So you can see in the diagram, this is the cavity is there on which the pressure, external pressure is applied, and this is the diaphragm or movable plate. So as the pressure is applied, this movable plate shifts. Anoic or fusion bond and dielectric isolation. So there is a stationary plate, metallization, reference pressure inlet. So the deflection of this plate will corresponding to the change of capacitance, which will be measured in form of pressure. So piezoresistive pressure sensors has a advantages like good linearity over a wide dynamic range, moderately higher pressure sensitivity, small size, high performance, high reliability, high yield, low cost. And challenges with piezoresistive pressure sensor: difficult in batch fabrication of thin silicon diaphragm, non-linear and unpredictable response to temperature sensitivity. Capacitor pressure sensor has advantages like pressure sensitivity is high, may be used for precise measurement of extremely low pressures. Temperature sensitivity of transducer is lower than piezoresistive counterpart. Of course, challenge: die area requirement is more non-linear than piezoresistive sensors, requires sophisticated on-chip circuitry to compensate the low linearity, often has a low dynamic range. Design consideration for device design like diaphragm mechanics, square diaphragm, circular diaphragm, you can choose. Loading condition like clamped aids, freely supported, and thin plate theory like small depletion theory or large depletion theory. So this is all your choice to be considered. Like in aeroplanes, jet engine wings has a MEM sensor which can measure a huge amount of the jet engine's pressure. Analytical modeling of circular diaphragm piezoresistive sensor under different loading conditions. So of course the COMSOL 3D software is used, and you need a finite element method to analyze the pressure sensitivity of the MEMS device. M is to find a optimal positions of sensing resistors for both the loading condition. Since the desired response is linear, small depletion theory is used. Diaphragm under consideration is of circular and this figure shows the small depletion of circular plate and the physical configuration of the pressure sensor and circular circuit on a membrane suspended on a silicon substrate. Least R sensor is a piezoresistor that changes resistance with the strain of membrane across with which a pressure differential is applied, and this the Wheatstone quarter bridge circuit used to change the change in resistance of a R sensor. So you have a different way of this is a Wheatstone bridge. So the bridge will be balanced if all the 4 arm resistors are obey these conditions, bridge balancing condition. So as the pressure will change, the bridge will become imbalanced, and this phenomena can be used to design a sensitive electronic pressure sensors. This slides correspond to the design parameters based approach for detailed and behavioral analysis of both normal and touch mode capacitive pressure sensors. So this is the circular diaphragm, which you can see it. So both upper and lower plate is made up of silicon. Insulation layer is made up of silicon dioxide. Schematic representative capacitive elements of sensor where T is the plate thickness, D is the cavity width, and Tox is the oxide thickness, and R is the radius. And having said this, another emerging area of fiber sensor. So you have this in this diagram, a 1D, 2D, and 3D type of periodic structures, and they have a refractive index variation in one direction, two direction, and three directions. So they are called as a photonic crystal fiber. So photonic crystal fiber may be in the rectangular shape, it may be the form of circular shape. So this is the diagram of periodic dielectric mirror. And this is the diagram of parallel dielectric rod and square lattice. So they have a spacing A. This is the hexagonal lattice of air holes in dielectric medium. So there are various shapes of photonic crystal fiber which can come across for very high sensitivity detection of chemicals and gases. A brief history of photonic crystal fiber. 1970 idea that a cylindrical light can guide a light approach that is. In 1991 idea that light coupled be trapped into a 2D photonic crystal made of silica capillaries. How? By drilling microscopic holes inside a silica rod, then drawing it to fiber. In 1995, theoretical proof that band gap guiding is possible. In 1996, first photonic crystal prototype was fabricated by the Russells in Southampton University, UK. How? By staking a silica capillaries, then drawing to fiber. Index guidance was 0.2 in that case. A brief history. In 1999, first hollow core photonic crystal fiber were demonstrated experimentally by again the Russell group of Southampton University, UK. Photonic band gap guidance, stack and draw techniques, 3 centimeter long photonic crystal fiber was drawn by MCVD method, modified chemical vapor deposition method. When illuminated with white light, you can get a different color of light because of band gap which is arises, and light will be trapped in this band gap phenomena. So photonic crystal fibers, two main classes of photonic crystal fibers are there. One is the high index core fiber. High index core fiber where the core of optical fiber is having a periodic air holes, and photonic band gap fiber where the holes are surrounded with and cladding both. But in case of high index core fiber, the cladding is not having a air holes, it is intact basically. So this is again high index core fiber. This is again has a 3 categories like highly high numerical aperture fiber where core is very large and cladding is very small. Large mode area fiber, this is the hexagonal shape of the pattern which you can see of fiber core. So large mode area fiber and highly nonlinear. This is the highly nonlinear fiber which is having some different shapes and different pattern of air holes. Similarly, this photonics band gap fiber is also low index core, hollow core, and black fiber. These are the 3 categories. So these are the some sorts of categories of photonic crystal fiber which you will come across when you study the literature on photonic crystal fiber. The other name of photonic crystal fiber is the holy fiber also, which is used in USA, but in Europe it is called a photonic crystal fiber, and in Far East country like Japan and Taiwan it is called the microstructured fiber. So high index, what is the role of high index core fiber? Light guidance by means of modified total internal reflection. Again, of course, basically what happens, you get some periodic structure like that, then you get a band gap properties, and these band gap properties can be utilized for low dispersion, zero dispersion, and zero attenuation properties. So if you launch a white light to the photonic crystal fiber, you may get a blue light in the output, and other lights will be trapped. They will not emitted by the structure. This is due to the band gap property. So white light you have incident, you are getting a blue light. It means that band gap arises in the blue light. I mean blue light has no experience of any sort of attenuation as well as dispersion. So photonic crystal fiber does not have this attenuation as well as dispersion. Introduction of low index capillaries in the cladding area effectively reduce the refractive index of the core surrounding area, allowing the total internal reflection. So low index capillaries like air channels are introduced in regular fiber by some capillary stacking techniques, and high index material like silica glass are remain as in this diagram, and the light is guided by this structure by using a band gap properties. Photonics band gap fibers. In most cases, the core has a lower refractive index than the cladding area. So even when we see that light is guided by high refractive index core, low refractive index cladding, this is not true for the case of photonic crystal fiber. Light is basically guided by low refractive index core and a high refractive index cladding, because you are getting a guidance by the band gap property, not by the total internal reflection property. So basically this pointing vector direction is reversed for the case of photonic crystal fiber. So your total internal reflection phenomena you're not guiding, you are guiding by the reflection of light, not by reflection of light. So true photonic crystal fibers, light guidance by means of light trapping in the core due to photonic band gap zones of the cladding. So reflection phenomena is actually in a other way around. For the case of photonic crystal fiber, cladding structure must be able to exhibit at least one photonic band gap at the frequency of interest. So hollow core fibers, you can see in this FEICM scanning microscopic images, the attenuation of this structure is quite high, 10 dB per kilometer. Losses of silica is 0.2 dB per kilometer, and the band rate, cutoff frequency, effective refractive index, all these properties are mentioned in the slide. And you can see for very narrow band of frequency, all the wavelengths are passing out from this structure. This is one of the most important property of the photonic crystal fiber. And when you can study the band gap properties, you have come across with this type of normalized frequency diagram, where propagation occurs, two different propagation regions like point A, where total internal reflection, point B is a band gap based. So another category of photonic crystal fiber is a solid core PCF. So attenuation is basically 0.5 dB per kilometer for this case. Effective refractive index and air packaging efficiency is already mentioned. Index guiding is robustness. So you have a different numerical aperture, different B number of optical fiber, number of modes supported by the photonic crystal fiber is also depends on the B number of fiber, and other phenomena is basically remain same, but the guidance mechanism is slightly different for the case of solid photonic crystal fiber. So advantages of photonic crystal fibers are many physical property can be engineered, like power fraction, birefringence, chromatic dispersion. The waveguide dispersion can be engineered to have a zero dispersion wavelength at any wanted wavelength. Fill with gases or liquid to make an optical gas sensor. Of course, you can develop a very good gas sensor by using photonic crystal fiber, because when you dip a photonic crystal fiber in the chemical, or when you gases are filled in the air holes, air passages of photonic crystal fiber, then you can get a substantial amount of sensitivity, because the gas molecules are trapped inside the photonic crystal fiber very easily, because they have a air holes, and very good this capillary is there, like flow tube is there, through which the gas molecules can be easily trapped to the photonic crystal fiber. And chemical sensor, of course, the same way chemical sensor can be developed, and they are demonstrated to be a very successful. Actually, they are able to detect even one single molecules in the gas elements. While changing the core diameter of suspended core fibers, the zero dispersion wavelength can be shifted to the visual region. Little bit fabrication we should talk about of the photonic crystal fiber. So capillary stacking is technique used to fabricate a photonic crystal fiber, and I would say that CGCRI Kolkata, they are the one of the very successful manufacturing of photonic crystal fiber in India. And they are running with different international R&D projects, and their technology were transferred to other countries also. And I visited personally the CGCRI. I would suggest some of you may also please visit the CGCRI Kolkata if you want to see how the photonic crystal fibers are fabricated there. Drilling, extrusion, soft glasses and polymers, capillary stacking techniques. So basically you have to have one hollow glass tube, and then you have to pack this hollow glass tube via silica capillaries, and then put into that MCBD method for this layer formations, and collapsing the fiber into the form of rod, this preform, and then put them into that fiber drawing machine to get the photonic crystal fiber. Capillary stacking is reduce the dimension of silica capillary from 1 to 3 centimeter to 1 mm using a fiber optic drawing tower horizontally stacked in an hexagonal configuration. So in that way we can actually practically develop the photonic crystal fiber. And extrusion means used to fabricate the majority of soft glass or preforms, telluride, chalcogenide, lead, silicate, bismuths. Molten material is forced through a die used to fabricate the first nonlinear solid core photonic crystal fiber in 2002. Lead silicate glasses to this specifications. And summary of fabrication techniques is as follows. So first you have to put one hollow glass tube in a preform in the form of hollow glass in the lathe machine, and then you have to pack this hollow glass tube by this silica rods of 20 mm dia, packed it fully, and then again preparation of each capillary, assembled of capillary to the desired structure, preparation of preform and fiber drawing. So these are some of the systematic process of fabricating a photonic crystal fiber. So summary of fabrication technique, variational of techniques depending on the preform materials, chalcogenide fibers, polymer fibers, compound glass fibers, variations of techniques depending on the fiber layout, honeycomb structure, hollow core fiber kits. Then photonic crystal fiber applications like light guidance for lambda that silica strongly absorbs in infrared range, high power delivery, gas filling the core, sensing nonlinear processes. Nonlinear effect can be easily excited for photonic crystal fiber, gas lasers like hollow core fiber lasers, doped core, in fiber tweezers, nanoparticle transportation in the hollow core, tunable sensors like liquid crystals in photonic crystal fiber. These are some applications of photonic crystal fiber demonstrated in this slide. These are some comparison of their transmission spectrum. Transmission spectrum of photonic crystal fiber can be obtained by using an optical spectrum analyzer. So you have to have one light source, which should be a single mode laser, DFB laser, and then you can use a optical spectrum analyzer to see the power in the transmission mode, and you have to be characterized of this nanotechnology component by using a FESEM, atomic force microscopy, and so on. Sometimes XRD and Raman is also required for finding out the thickness and morphology of the core and deposited materials. So hollow core photonic crystal fiber, solid core photonic crystal fiber, and Bragg fiber, these are some of the categories of the photonic crystal fiber. And this was my last slide for today's talk. And thank you very much for giving me this opportunity for speaking to this FDP program. And I hope this fiber optic technology will be quite useful for all the listeners who want to really work in this domain. And I would like to say one thing, that there is no discrimination between material science, electrical engineering, electronic engineering, and photonics. Now all these branches are merged to each other and create one interdisciplinary area, and there is no constraint of fabrication technology also. Now you can fabricate optical components along with microelectronic component on the same substrate without any challenge, fabrication challenge. And then thank you very much for the invite. And now I think we are open for discussion.
So all the participants, please, if have you any queries, please ask.
I think it was 4:15 p.m. when
Yes,
that
sir.
has to be end up. So please ask any question if you have.
Hello, sir.
Yes.
Sir, what are the present research scope in biosensor?
Actually, biosensor is attributed by the photonic technology in a quite large perspectives. And if you heard about a surface plasmon resonance sensor, SPR sensor, now they are supposed to be one of the highly sensitive sensors which are targeting this biosensing applications like COVID-19 virus detection. So SPR-based sensor are nowadays people are working on that, and it has the capacity of detection of single molecule out of 10 to the power 6. I mean, out of 10 to the power 6 molecules, if you have one adulterated molecules, then fiber optic SPR sensor has that much capability to sense it. So biological species, not only cancerous cells, biological species, DNA hybridization, pathological problems, blood group detection, all these now are going to address by the fiber optic surface plasmon resonance sensors in near future. And probably by 5 to 10 years later, you will find all these fiber optic SPR sensing chip in our laboratories also. I mean the pathological laboratories in the city, where the DNA hybridization, DNA molecular detections, cancerous cell detections, blood group measurements, and many other type of the test can be performed with very high accuracy and very high sensitivity.
Okay, I think Professor Ashish Ranjan from NIT Manipur would like to say something.
Yeah, please.
Sir Ashish. Ashish sir, is he audible? I think there's some network issues there.
Okay, no problem.
Okay, thank you, sir. It's a very nice session. Of course, it is informative. So, different type of sensor you have been designed and also explain their advantages and drawbacks in practical applications. So we are very much thankful to you for giving your interest to share research aspects on the topic of sensor. So I think our participants, those who are beginner, should start their research on the topic of sensor with the help of your valuable talk. So
yes.
Once again, I would like to thank from the Department of Electronics and Communication Engineering, NIT Manipur. So, on the depend on your valuable talk, we should start our new research way, and in future we expect your help, sir.
Thank you very much for giving me the opportunity to speak on this DP program, and I hope that this NIT will be working on this fiber optic related research domain, and I also hope that some of the faculty is already involved in the research, and if they want, they can collaborate with me also in near future, and we can develop the sensor jointly, and this will be helpful for exchanging our ideas along with our expertise between these two institutes. And I invite some of faculty to my institute also in near future for collaboration, research collaboration, and exchanging the students for their masters and PhD degree.
Ashish sir.
Is it audible, sir?
Actually, sir, your voice, please speak loudly, sir. It's not clear.
Good evening, sir. Sir, Ashish, sir. From,
yes, Ashish, I recognize.
Yes, sir. For we people, sir, advise something. We are we are just doing this CMOS like that type of thing, sir. So what we can explore from this type of chemical sensing?
Yes.
What are the first area that we can move forward?
Yes. Actually, I have developed this facility from 3 to 4 R&D projects. And, I have a collaboration with RRCAT Indore as well as CSIU Chandigarh, and I am getting a fiber optic rating from RRCAT Indore. Otherwise, FBG is very, very costly. You cannot buy it from Thor Lab USA. So I would suggest Ashish to collaborate with some CSIR labs, some government funding agency, so that you can develop some experimental facility in the department for developing a fiber optic sensors. And my expertise will also be there if you want. And I can visit your NIT in near future also to see the departmental facility and which faculty is involved in which areas. And this is the very good opportunity for between us to work together. And actually, my second thing is that there is no discrimination between microelectronics with photonics nowadays. As you told that the CMOS technology, some of you are working, and how will you come to the photonics domain? So that type of the constraint is no longer valid. Now you can fabricate, you can develop a MEMS device with photonic device on same silicon substrate. I mean, whatever electron beam thermal evaporation system I am using for deposition of components on fiber optic on fiber, the same process, same electron beam thermal evaporation system can be used for developing a microelectronic chip. So there is no demarcation line between these two areas, and same development sensor development process can be used for microelectronics technology as well as for photonic technology as well, with some constraints. So I would say that to collaborate with some research lab to learn the expertise there and so on, that will be very, very much useful for all of you to work in this domain.
Thank you, sir, for your kind advice. And sir, in near future, I will definitely come to you and see your lab. So,
yeah.
Thank you, sir, for giving a nice talk in our college, sir. And in near future, we are also looking for your valuable talk, sir.
Yeah, sure. I will always be there.
Thank you,
If lockdown will not be there, then we can move physically from one place to another.
Yes, sir. Yes.
Since I think you are from Dhanbad, so you can easily access IIT ISM, and you are alumni of the IIT ISM, so that is also not a problem. This is your alma mater, so you can access this my lab also.
Thank you, sir. Thank you, sir, for your kind words.
So, sir, can you share PPT, sir? Okay. No, sir.
By email?
Through mail.
I will send you. I will send you on the same email ID.
Okay. Sir, am I audible, sir?
Yes.
Okay, sir. You can send it in my email ID. This is fdp.ec ATM.
Yeah, sure. I will send you after.
Okay, sir. Okay, sir. After that, I will share with all the participants.
Yes.
Okay, sir.
Okay.
Thank you, sir. Have a nice day, sir.
Yeah, thank you very much. See you.
Welcome, sir.
Okay, bye.
Mm-hmm.
Mandal sir. Hello, Mandal sir.
Yes, sir.
Tomorrow microelectronics.
Sir, sorry, sir.
कल क्या है microelectronics field.
Microelectronics.
So you are doing a very good work, sir.
Yes, sir. Yes, sir. Yes, sir. Tomorrow my microelectronics.
Okay, Mandal sir.
Not tomorrow, sir. Day after tomorrow, I think.
Day after means okay, sir.
Yes, sir. Yes, sir.
How are you, sir? Fine.
On 21st.
Monday, sir.
Hi, sir.
Fine, na.
Corona just, sir, progressing, sir.
Okay. Take care.
I will try, sir, after complete this one to come to sir.
Okay. Okay, sir.
Okay,
tomorrow
sir.
We will again meet.
Okay, sir. You are joining, sir. It's my pleasure, sir.
From first time also joining substrate integrated circuit.
Of course, sir.
But actually, tomorrow also I will join.
Okay, sir.
I will join. Okay.
Okay. Sir, give your attendance, sir.
Attendance I am not doing because I am not a participant. That's why I am never doing any attendance for last 2 days.
Okay, sir. Just I am joking, sir.
Okay. There is some free or what? Free this one.
Okay, sir. Thank you. Thank you all.
Okay.